Okay. Hello, everyone. I hope you guys are good, and welcome back for those that were with me last time, and for those that are here the first time, thank you for joining us. I'm just going to apologize in advance if in case we run into trouble like the last time, but I think I'm more prepared this time, and we should not have any problems. I'm just going to give you guys give each other like a minute or two, just to make sure that you're all settled and connected. Cool. So just like we discussed last time, if you check at the bottom there of your screen, you should be able to see some useful stuff there, which includes the reactions. And I would like you guys to use that. If maybe when I ask if everyone is following, could you just press there and just give me a thumbs up so that I'm sure that everyone is following. And also, if maybe you've got a question that you want to post in the chat group there, there's the chat function there. You can just press there and send your message so that at least I can see. In case maybe when you want to ask the question, I'm looking this way and I cannot see that you've got a question there. So that means sometimes I might take a little time to get back to your question if maybe you post the question while I'm facing this side and I only then see it a bit later. So it also helps that when you've got a question, can you just give me a reaction in the group so that I can get your attention, and then I will go to your question and answer it, and hopefully that will be helpful. Okay, cool. So, okay, I think it's time now. I'll also try for a break, maybe after an hour and 30 minutes, but we can have a small break, 5 minutes or so. Hopefully we'll not be behind time. Cool. Before I start, then can I just get like a thumbs up to make sure that everyone is ready for us to start? Okay. Almost everyone gave me a thumbs up. So yeah, I think we're ready to start. Cool. So today's workshop is going to be focusing more from the bivariate moments and going forward to up until convergence. Because I understand that your test one is going to be end towards convergence, which is actually the first time that that section is going to be in a test one. But anyway, okay, let's do this. So remember now in this section, we are dealing with a vector, right? We're dealing with a vector Z, which has got two random variables, X and Y. Initially, we were looking at a random variable X or random variable Y independently, right? That is as a unit on its own. But now we'll be considering a vector, which has got those two random variables, X and Y. A vector can actually have more random variables, but at this stage, we only limit them to two. Hence, we are dealing with just our X and Y. And the same way that we were able to find the expectations and other important properties of the univariate case, we are also able to find the same for the bivariate case that we're dealing with. If we were to start with the expectation, I'll start with the expectation. And if we consider the expectation of some function g of x and y, like this here, right? Okay, so these markers are still quite new and they're still quite a little bit thin, but yeah. If we're considering the expectation of some function g x of y here, which has got two random variables in it, this will be equal to the summation, right, with respect to x and y of this function that we have here, multiplied by their joint PMF like that. And in a continuous case, would instead be integrating the same function that we have here, multiplied by the joint PDF of x and your y. Right. Again, this will all depend on whether you're dealing with a discrete case or a continuous case. So as if you're dealing with a discrete case here, this is what you would use. If you're dealing with a continuous case, this is the formula that you would use. And just to point it out, even though this is quite obvious, this is not the formula of expectation, but rather a special case of expectation, right? Where we use the law of the unconscious statistician to say, though you have information about x and y, now you want information, in this case, the expectation of some other function g, which is in terms of your x and y. Cool. Then that's just the first property that we would consider under the bivariate case. The next one, which is one of the most important under this topic, is the concept of your covariance, right? And the covariance actually just measures the strength. It measures the strength of a linear relationship. Because remember, in this section, we are dealing with the two random variables. So when we now consider covariance, we're trying to look at how strong the linear relationship between the two variables that you have there is, right? And the first thing we'd know is that by definition, the covariance of the random variable x and y, which we sometimes denote like this here, is defined as the expectation of x minus the mean of x multiplied by y minus the expectation of y, like this. This is a definition of your expectation, which can be simplified as the expectation of your xy minus the expectation of your x times the expectation of y. It's very important for you to know. It's very important for you to know these definitions here, because there come some questions which, by simply just writing out this formula and getting to this point here, would simply just simplify your whole question for you. Okay, cool. Then the next thing is just the interpretation, which is something you hardly get from a lucid, but it's also just important to understand that if your covariance between your x and y is greater than 0, this simply just means that there is a correlation, right? There is a correlation, but in a case where the covariance between your x and y is equal to 0, there is just no linear relationship between the two. And then in a case where it's going to be less than 0, right? When it's less than 0, then this relationship that you have there is negative in this case. So you do have a linear relationship, but it's negative. And in this case here, I should have written that this one here is positive, right? This is something that's just important to know for your own understanding of the whole concept of covariance, but it's something that I've not yet seen where you actually have to then interpret what it means to have a certain value of your covariance. All right, cool. And the next thing are just a few properties under covariance, which are quite important. And the first one, so now we're looking at some properties of covariance of your x and y, still looking at the vector, which has got your x and your y. For A and B, which are just elements of the real number, so these are just constants. Whenever you see an A and B on what I'm going to write now, just remember those are just constants. Cool. And the first one is that the covariance of your x and x is simply just equal to the variance of your x, like that. And similarly, if you're dealing with y, the covariance of y and y will just be equal to your the variance of x. This is actually very important, more than it looks, more than you can realize here, because there could come a time where instead of just being given x like this, you could be given maybe for you to find the variance of let's say 2x plus y, like that. Instead of, if it's difficult, especially in a case where x and y are not independent, this is just me going too forward, I guess. But I'm going to explain this further, what I'm saying now. You would be able to use this here by knowing that whatever variance that you may have here, you might actually then just translate it into being a covariance problem. And once it's a covariance problem, then you can use this definition to answer your question. Then the next property is that the covariance of x and y is simply just the same as the covariance of your y and your x. And the reason this is important is that in a case where maybe you're going to do some expansion to your covariance problem, when you then come across a case where one term has the covariance of x and y, and the other term there has the covariance y and x, this is the same, which means that you can always add them up together and reduce the number of terms that you have in your equation. And the third one is that the covariance of ax and y here is the same as the a times the covariance of x and y, which is the same as the covariance of x and your y. Again, remember, this a here is what I wrote here initially as just being some constant element of the real numbers. So what this is saying is that if you've got an a here or an a just before your y there, it's the same thing. And with that, you can simply just take out your a out, and this would be your answer. Then one of the most important ones, which is that the covariance of your x plus y and some other random variable z is simply just going to be the covariance of this x here and the z, covariance of x and z, plus the covariance of now the y and your z. So you, in a way, you are distributing this here to your z that you have there. And to go back to what I was just talking about, when we now consider a variance case, right? I am now going to prove what the variance is. The only reason I'm doing this is so that we can see the important one, or how we use these properties that I've listed now here. If you are asked to find the variance of, let's say, AX plus BY in this case here, right? Initially, like last year, you would find that the cases where you would just this is equal to the variance of AX plus the variance of BY, and then you're going to check out your constants and square them. But in a case now where we're dealing with these bivariate random variables, which in most cases would actually not be independent, which means we cannot use that formula where you're just going to say this is equal to the variance of that plus the variance of that, right? We can then translate this to what I was saying earlier on there, that when you're given a problem like this, you can translate this to instead just being a problem of the covariance of AX plus BY and AX plus your BY, like that, right? So that's what you would do there. You translate your variance problem to being a covariance problem, and then now we are going to start applying these properties that we've mentioned here. And as much as this may be a little bit redundant, this is very important that we do this because a lot of questions you would have to apply this. So I just want to make sure that we're all on the same page on how we apply this, so that when we get to examples, we know exactly what we'll be doing in that case. So the first thing that you can start is to start by distributing this here out, so that you have the covariance of AX and AX. Oh, I'm sorry that this is now the same size. So it will be the covariance of your AX here and your AX plus BY plus the covariance of your BY and your AX plus BY, like this again. So all I've done here is to distribute this here and that there, which is exactly what we were doing when we were doing this other property, our property number 4. This will be equal to, again, you can distribute this again, such that you have the covariance of AX and AX. All I've done is to take the covariance of this here and that, plus the covariance of the same AX again, but now with our BY, like that, plus this will be the covariance of your BY and AX, right? Just this and that, plus again, the covariance of the same BY, but now with this other BY that you have there. Now we'll go on further to use our properties to simplify this into something that's more user-friendly, right? And the next step would be that this is equal to the covariance of AX and the covariance of AX again, and AX and AX. Remember, when you've got a constant, you take it out. But now that we've got the constant on both sides, that will be us taking out the A one time and then again, which means we're going to have an A squared there, and we'll end up with the covariance of X and X, which we say the covariance of X and X is simply just equal to the variance of X, like that. Plus, now we'll have our A and B there. So we'll take the A out, like we said, we'll take a constant out, and B again is also a constant, so we'll take both of them out. So now we have AB and the covariance of your X and your Y. Plus, we'll do the same thing there. It's your AB out, and you're left with the covariance of Y and X in this case. Plus, we take the B's out, similarly the way we did with our A's there, so that now we'll be left with just B squared and the covariance of Y and Y, which we now know that is simply just the variance of Y, right? So now I'm just going to simplify this as you have it in your notes by starting with A squared, the variance of X, plus B squared, I hope you can see this, B squared, and the variance of Y, which is what I have here, plus, now this using this property here, right? We have our X, AB covariance of X and Y, AB covariance of Y and X, and we've established that this is actually just the same thing. Hence, we have 2AB and the covariance of your X and Y. Okay, this is covariance of X and Y, like that. So this is what you have in the notes, that the variance of X, AX plus BY is simply just going to be equal to A squared variance of X plus that, and then you end up having a final answer like this. Again, this is something in the notes, but the reason I did this is because being able to do this here is very important, as you'll see as we go on further and start looking at examples. All right, cool. And in a case where your X and your Y are independent, this term here will disappear. Again, that's something that we're quickly just going to look at pretty soon. And then the next property under the bivariate case that we're looking at now is the concept of a correlation coefficient. The correlation coefficient, right? And this here is simply just going to be equal to the covariance of your x and your y divided by their marginal standard deviations, right? So you've got two random variables, x and y, and you're asked to find the correlation coefficient. The first thing you need to find is the covariance of your x and y, and then after that, you're going to divide with the marginal standard deviation of each of the random variables. And then this here, note, it's quite important, note that if your x and y are independent, right, then the covariance of x and your y is simply just equal to 0. Again, this is very important in the sense that this line, the arrow that I drew here, is only going one way, right? Which means for the covariance to be equal to 0, this had to be the case in the beginning. Your x and your y are independent, and therefore the covariance will be equal to 0. But the covariance being equal to 0 will not necessarily mean that your x and y are independent. So if you are asked to find, maybe the question is asking you if x and y are independent, for example, right? If you just find this here and you get your answer to be 0, and then you conclude that therefore x and y are independent, that would be wrong because this arrow only goes one way, right? So in a case where this question, suppose this was a question in a test and you were asked to find the variance of that. If we were given information earlier on that x and y are independent, then we would know that the covariance of x and y, in this case there, would be 0, which means that our variance of ax plus by was simply just going to be this term that you have there, right? But again, that is only if there was something that was telling us that the x and the y there are independent random variables. Cool. The next thing that we're going to look at is an example, just to demonstrate all of this out quickly before we go to the next concept. And this is something that's very important. That's probably good. That will definitely be in a test as well. So you need to be very comfortable with it, to an extent where you will not even have to think very much when the question comes up. So if we look, considering an example like this here, okay, and the easiest distribution of them, or where your x and your y's are going to be some exponentials, right? Let's say now your joint PDF that you're given is this here minus x minus y, your x is greater than 0, your y is greater than 0, and this is 0 otherwise, right? And what the question is asking us to find is for us to find the correlation coefficient, find the correlation coefficient between x minus y and x plus 2y, like this, right? So this is what we were given, that find the correlation coefficient between your x and y, and then we are given this marginal joint distribution of your x and y. So by definition, right, we already know that this will simply just be equal to the covariance of x minus y and x plus 2y divided by the marginal standard deviations of x minus y and your standard deviation of your x plus 2y. So for us, let's just start by finding the denominator of the formula for the correlation coefficient, which in this case will simply be the covariance between your x minus y and x plus 2y, right? And we will use our properties, right? So that this here will simply just be equal to the covariance of x and x plus 2y, like this, plus the covariance of minus y and x plus 2y. Again, nothing fancy that I've done here. All I've done is to distribute my x to that, my minus y to that, right? And I will go on further again to distribute my x to this here, so that I will have my covariance of x and x plus the covariance of the same x here and 2y plus the covariance of minus y and x plus the covariance of the same minus y and 2y, like that. I could have already by now taken this minus out here, but just to be safe, to make sure that you still have the negative here, I've kept it as a negative y there, because sometimes you can easily make a mistake by taking this minus y there and then end up just having a minus y on one of these terms and this being positive. Whereas both of them, whatever you distribute this minus y to, will also have to be affected with the negative there. Which means now, using the properties again, this here will become the variance of x plus, this is a constant 2, so we take that out, and then we have the covariance of x and y. This will be minus, because that's a constant that's between that y there, and that constant is a minus 1. So I'll take that minus there, and then what I'll be left with is just the covariance of y and x, and then I'll take the minus again there, and I'll be left with the variance of my y, right? The reason why this will be the case is because when I take the minus out, I have a minus the covariance of y and y, which by now we all agree that is just simply equal to the variance of your y, right? So now this is what we end up having from this here. We now just have that this is equal to the variance of your x plus the covariance of your x and y times 2 minus the covariance of your x and y minus the variance of y, right? And in a way here, I cheated a little bit because I used a case where the marginals are just exponentials with the lambda 1. This is something that you can always verify later. But my x here is actually just exponential, and my lambda is equal to 1, and my y is also exponential and is equal to my lambda equal to 1. So under normal circumstances, when you get to this point here and you want the variance of your x and you want the variance of y, right? Under normal circumstances, what you would have to do is that you would have to draw your region. You draw a region. And the reason I'm saying draw a region is because you would have been given this joint PDF, right, which is defined as follows. So you would have to draw your region, right, and after that, you have to find your marginals. You would have to find your marginals, the marginal distributions, right, because you're given a joint of your x and y. Okay, sorry, there's a question in the group. And what happened to the 2 on the last covariance? Oh, sorry. Okay. The last covariance. Oh, this is supposed to be 2 here, right? Okay, that's my bad. Thank you for that. I don't know if you guys saw that we had the 2 here and we took it out. Then we had this term, but this term we have 2 constants, the minus 1 and the 2 that's here. So we're supposed to take both of them out and then have a minus 2 there. I forgot. I made a mistake there. Thanks, man. Cool. So under normal circumstances, right? After when you get to this point, because now you would want the variance of your x and you also want the variance of your y, right? What you would have done here is to then draw your region, because you'll be given some region defined as follows here, and then you would have to find your marginals. And when you're done finding your marginals, you would then have to find your expectations, yeah, and your variance, basically. Because after that, let's say, hey, this is the joint that I have here. I will draw my region. I will find my f of x, and I'll find my f of y. And then from then, you just use your simple rules of finding your expectations and your variance, right? But because of this example that I chose, it's easy to see that these are exponentials, right? Obviously, in a test, you have to do this process to show that, okay, these are exponentials. And also, an extra thing you would have to do, right, in this case is after finding your marginals, right, it's always worth trying to find out if they are independent, right? That is, after you find your marginals, is the f of x multiplied by f of y equal to fx of y, right? And if so, like in this case of the example that I have here, because when you separate these two, you're just going to have your marginals like this here, your for x and your y, and clearly these are independent. And the moment they're independent, it means this term and that term there will simply then just be equal to 0. Those two terms there would be equal to 0. Because remember, if x and y are independent, then the covariance of your x and y will then be equal to 0. So what I would just be left with would just be the variance of my x plus 0 minus 2, the variance of my y, like this, right? Of which we know by now that the variance of x in this case, which the marginals are supposed to be exponentials in this case here, with my lambda equal to 1 for each. So what I simply just have there is a 1, and I have plus 0 minus 0 and a minus 2 plus times 1, right? So my answer in this case would simply just be equal to a minus 1 for my covariance between my x minus y, x plus 2y, like that. So what was very important there is when you get to this point, you need this term and you need that term, right? Which means in most cases, you're going to have to draw your regions, find your marginals, determine whether f and x actually independent or not, so that you would know if this covariance is equal to 0. And because this is so much work, in most cases, this will be the case that your X and Y will be independent, but it's something that you might either be told or you'd have to go through this process to determine if your X and Y are actually independent or not. But remember, this was just the numerator, right? The covariance of your X and Y. We also still need the marginal standard deviations of your X and minus Y, and also for your X plus 2Y, which means for this, remember the standard deviation is simply equal to the square root of the variance. So we'll first need to find the variance of your X and minus Y, right? Remember there's a formula that we proved earlier on about such cases, but in this case where I know that my X and my Y are independent, right? Why? Because I've proven it already. If this was in a test and you've gone through all these processes, this then will simply just be equal to the variance of your X plus the variance of your Y, right? And similarly, for the other term there, the variance of your X plus 2Y would simply then just be equal to the variance of your X plus the variance of 2Y, which is simply just the variance of X plus 2 squared, the variance of Y. Cool. Okay, then there's a question here. There's a question which is asking if we could have been able to solve these terms, the covariances, if they were not independent. Yes, you would have been possibly able to solve it, but that means you are going to be using these the formulas. This formula that the covariance of your X and Y will be equal to the covariance of X minus the mu X minus the mu of X and Y minus the mu of Y, like that, which will be very complicated. That's why I said that in most cases, if you were to look at your examples or any other possible questions that you could come across there, it's mainly that your X and Y will be independent. But the only way that is going to make you work for those marks there, since you hardly have to use this question in a question like this, is through that you would have to draw this, find your marginals, and maybe show that these are independent in most cases. So yeah, in a case where maybe it's really rough on you guys and you find that you need to find a covariance of X, you just have to then try and work around to see if you can find anything with that formula. And remember, this is also equal to the expectation of your X and Y minus the expectation of X multiplied by the expectation of your N, like that. And this is something that actually you are able to do, because now that I think about it, there's a TAT test, one of you guys' TAT test that I came across where there was something about the covariance of your xn, something like this here, where you then have to find the expectation of your xn minus the expectation of x, expectation of n, where this year there was some conditioning that you had to do initially as the expectation of xn given some n is equal to n, something like this. But anyway, we're not there yet. But my point is just, if you had to find this, there would have been extra information that would have been given that would be able to help you to find an answer to something like this, as he did in this test that I'm referring to. I'll try to remember which exactly it was so that you can refer to it. But in that case there, the first question wanted you to find this part using some conditioning. So yeah, basically that's what you would have to do in a question like that. And just to finish up, I hope that answered the question. And just to finish up this question that we're then answering, then this part here, in our case, this variance of x was equal to 1, as we saw. This was also just equal to 1. Then this here was 1, that was 1. So what we had here is just 1 plus 1, which is 2. Then here we just have 1 plus 4, which would be equal to 5. So which means that this correlation coefficient between this and our x plus 2y that we wanted would then simply just be equal to minus 1 over the square root of 2 multiplied by the square root of 5. Something like that. Anyway, but then again, this here, for our example that we're doing here, does not really matter. What I wanted you to understand the most is just how you would approach answering such questions like this, right? Cool. I'm just trying to see if there's anything else important that I left out under this concept before I move on. Okay, the thing, okay, there's a point I wrote here. We've spoken about this already. Let's just remember that if maybe that happened in a case where, in this example, we found that the covariance between our x minus y and our x plus 2y, suppose maybe we found that somehow that's equal to 0. A note I wrote here was just that, remember, this does not mean that these two here are independent, right? Because remember, for this to be true, they have to be independent initially, not the other way around, that this is equal to 0, and therefore you conclude that these here are actually independent. Cool. All this would just mean is that there is no linear relationship between these two terms. But again, this is in a case where this was equal to 0, which in this case it was not equal to 0. It was just simply minus 1, which tells us that there is a linear relationship, but just that it's a negative linear relationship between that. Okay, guys, and that's basically what I have under covariance between two random variables in one vector z, right? Can I just get a thumbs up to make sure that you guys are still with me, and also for you guys to allow me to go on to the next concept of bivariate normal distributions. Cool, awesome. So bivariate normal distributions is the next part. And this is also another important concept, which will definitely be in a test with quite an amount of marks. There are just a few things that are very important for you to remember for this section. And okay, the first thing, and also we're still going to look at conditioning later, but I'm just going to quickly tackle the conditioning under the bivariate normal distribution. So when we're done with the bivariate normal, then it's just done for good. Cool. So suppose we say that your fxy, right, we've got a joint distribution of your x and y, right? And we're saying that it has a bivariate normal normal distribution, right? Distribution. Okay, I'm just going to write it something like that. It has got a bivariate normal distribution, right? Which means your x and y, right? Because remember, this is a bivariate case, so we are dealing with a vector. So this just means that this vector that you're dealing with here, we are saying it's got a bivariate normal distribution with mu and this covariance matrix that you have there, right? So I just want to quickly interpret what this actually means for our marginals, your x and y, right? So the fact that this vector that we have here of x and y has got a bivariate distribution with these parameters there, this then already tells us that your marginals, your fx and your fy here, are also normally distributed, right? So these are also normal. This could be helpful here and there. This is actually helpful. You're going to say why. So if your bivariate, fx and y, if this vector is got a bivariate distribution, then the marginals themselves also are normally distributed. But the other way does not go, is not true. The other way is not true. That is, if you've got two marginals, right, which are normally distributed, you've got your x, which has got a normal distribution, and you've got your y, which has got a normal distribution, for example, right? This does not mean then that this bivariate distribution, like this vector of x and y, is going to have a bivariate distribution, right? This only goes in one way and not the other way around. That's also just quite very important to note. So in a case where we say that we've got a bivariate distribution with x and y, they've got a bivariate normal distribution, the marginals are normally distributed, then the marginal, the PDF of x given a y, right? Hence I said I'm going to quickly then just tackle the conditioning under this section, is that the PDF of x given a y will also now be normally distributed with mu x plus the correlation coefficient multiplied by the marginal of x, standard deviation, and then that of y multiplied by y minus what you're saying given there, which is our y and its mean, y mean, like that, and the standard, the variance will be given like this, squared, like that. Again, this is not something for you to worry about, like writing it down, because it's something that's in your notes. So similarly, if you were looking at this PDF of y, right, but now given x is equal to x, this will also be normally distributed. But instead of having mu x here, you would have the mu of the one that you are interested in, plus the correlation coefficient multiplied by the standard deviation of this y, divided by the standard deviation of what you're given, the x, multiplied by what you're given, which is x in this case, minus the mean of that x there, and this variance will be the variance of y squared 1 minus the correlation coefficient or squared, like that. Right? And the reason why this is very important, because as you will see later on when we do a certain example, in a case where you're going to be asked like for a conditional expectation of whatever random variables that should be given in a certain vector, right? What's important are just going to be a few steps that I'm going to align for you to be able to get to this point. And if the question is asking for the conditional expectation, like I'm saying, all you would need is for you to then be able to evaluate what this point, this value would evaluate to. That's all you'd want to get to when you're not dealing with conditional expectation under this this section. And then also for probabilities, I'll explain the probabilities part with an example. And what's important to know is that when you've got a vector W, right, which is made up of, let's say, U and V, right, these are random variables, because in most cases, well, even though we'll be given something in terms of your X and Y, we are going to be translating this into just a simple U and V. I'll explain the reason why we'll be doing that. And we will say that this random vector that you would have would have a bivariate normal distribution, right? And the parameters will be given as follows: A times mu plus B, and then you have your A covariance matrix and A transpose, like that. So for most of these questions, most of the work that we'll be doing there will be for us to find what our A is in most of these cases, right? Because almost everything else will be given. This year will be given in a question, and this will be given. The two of those will always be given in the question. All we will mostly be looking for is our A, right? And finding A is something that we're going to look at quickly just now. Another important factor, another important note to write down under this section is that now, if we do conclude that something has got a bivariate distribution, right, then the correlation coefficient being equal to 0 will now mean that X and Y are independent. Remember, initially, just before we started this topic here, we were saying if you get, remember that this here is for X and Y, which is equal to, this here is simply equal to the covariance of your X and Y over the marginal standard deviations, right? Which means if this is equal to 0, therefore, the covariance of X and Y is equal to 0. So what this statement is basically saying is that if the covariance of X and your Y, right, under the bivariate normal distribution, if this is equal to 0, right, then you can conclude now that your X and your Y are independent. Unlike before, where we were saying if X and Y are independent, then the covariance between X and Y is equal to 0. Now, under the bivariate case, we are also now saying that even if the covariance of X and Y is equal to 0, which means that the correlation coefficient is equal to 0, if these two values are equal to 0, then you can conclude that your X and your Y are independent. Which means now you're able to answer the question of whether two random variables are independent, right, by simply just finding the covariance between the two random variables that you want to. But again, this is only possible under the bivariate normal distribution. Hence, I wrote this here first, that if bivariate, right, this is after we've all concluded and agreed that what we are dealing with there is the bivariate distribution, bivariate normal distribution. Bivariate normal, let me write bivariate normal. Because what we were dealing with before was also just a bivariate case, but now we're saying if bivariate normally distributed, then this here holds. Cool. Then something that I just want to quickly outline, the same way that I said that your mu and your sigma, your covariance matrix there will always be given in a question. The only time they will not give you that is if they were to tell you that, they will tell you that independent standard normal. Okay, let's say a standard normal. Okay, not standard normal. Let me write standard bivariate normal. If those are the right words, I'm not sure if I am saying them correctly. Standard bivariate normal, right? So anyway, my point was, in most cases they will always give you this and that. But if they just wanted to trick you and they will just mention that what so and so is actually a standard bivariate normal distribution, And in this case, they will not tell you mu and your sigma covariance matrix, because for a bivariate, you should actually just know that if x and y are bivariate normally distributed and are standard normals, right? This mu and your covariance matrix, your mu will still just be equal to 0, 0, and your covariance matrix will now just be equal to 1 and 0 here, and your 0 and 1, right? So this is the only case where you would actually need to know what these parameters are. Otherwise, in any other case under the bivariate normal distribution, your mu and your sigma, the covariance matrix there will always be given at the beginning of the question. Cool. Then the next concept is that a bivariate normal distribution, a bivariate normal, right? A bivariate normal can be written as a combination of two independent standard normals, right? So bivariate normal can, okay, I'm gonna write a lot here, can be written, actually, sorry, instead of writing this down, I'm just going to write it mathematically, right? That for a bivariate normal, right? So I am going to say this x and y here in this case are my bivariate normal, right? So this statement says a bivariate normal can be written as a combination of two independent standard normals. So there's a question here. Okay, cool. So what I'm saying here is that for a bivariate normal distribution, it can be written as a combination of two standard normal distributions. And mathematically, this will be written as this and this here plus mu of x and mu of y, right? So this is saying that if x and y, in this case, my x and y are actually a bivariate normal distribution, right? So this statement is saying if you've got a bivariate normal distribution, you can always write it, you can break it down into a combination of two standard normals. So in this case here, my Z1 and my Z2 are independent standard normal distribution, okay? And then the reason why this is important, this concept, not that you'll be asked to break down, or if possible you could, but what's important is that just this term here, which we call this, I'm not sure I can pronounce it properly, so I'm just going to write it down, decomposition, this matrix L, right? Yeah. So the whole concept about us being able to break down a bivariate normal distribution into a combination of two standard normals is then for us to introduce us to this decomposition, this L matrix, which if you're actually lucky, because I think it will be 3 marks if you're asked to calculate, to write down what this matrix is. This is simply you just finding the standard deviation of your x, and you have a 0 there, and you will have your correlation coefficient multiplied by the standard deviation of your y, multiplied by 1 minus the square root of 1 minus the correlation coefficient squared, multiplied again by the standard deviation of y. In case maybe I wrote something wrong here, you can always just verify this. It should be somewhere there in your notes. So this is something, it's only one instance where I saw a question which was asking a student to calculate what this is. But again, as you can see, this is quite simple. You just need to find the standard deviation of your x. You have the 0 there, and you have this term, and you have that term, and then you just write it down as a matrix, right? And another thing that you can also then use, if ever it would be useful, is that, like the same way we're saying that if you've got your x and y and the bivariate normal distributions, you can write them as a combination of two standard normals. Similarly, if you're able to write, let's say you're given some random bivariate distribution, not normal distribution. If you've got just this distribution here, a bivariate distribution, and if you're able to write it as a combination of two independent standard normals, then you can conclude that this here is actually a bivariate normal distribution. Cool. So before I get into a proper example, I just want to quickly go over what I've just spoken about here now. The first thing is just that we've got our standard bivariate normal distribution. This is how you would write it down, the parameters 0, 0, 1, 0, 0, 1, like that. Then there's this concept of your bivariate normal distribution, right? Once you know it is a bivariate normal distribution, we conclude that you can actually write this here as a combination of two independent standard normals, right? And this includes some decomposition that we actually have here, the matrix L, which you can find by doing that. Then there's this concept that if you've got a bivariate distribution and you're able to write it as a linear combination of some two standard independent normals, then you can conclude that that distribution that you have there is actually a bivariate normal distribution. So now I am quickly just going to do an example so that we can see how we apply what we discuss now into answering questions, right? This question that we're going to do is going to be broken into two. One, a probability question, and then one where you're asked to find conditional expectation. But the conditional expectation one, we are just going to more or less just talk through it because it's the same procedure. Then I'll just underline towards the end the most important part, which separates it from a normal probability question. So let's consider our example under this case, under this scenario. So like I said, you'll be given a bivariate distribution, in this case a normal bivariate normal distribution, and you'll be given mu, right? This is the mu vector, and then you're given your covariance matrix as follows, like this, right? And then the next thing, the first question here, okay, there's a question. Oh, okay, there's a question in the group here that I'm just going to quickly answer. There's a statement, the last statement I wrote here was saying, if you've got a bivariate distribution, right? A bivariate distribution, right? Because remember, when we were writing Z equal to like something like this here, this is the same thing, was this is some vector. So the last statement I mentioned there was that if you've got a bivariate distribution, not a bivariate normal distribution, but if it's just any bivariate distribution that you have, if you are able to then write it as a combination of two independent standard normals, then you can conclude, so it will be a conclusion, that it's actually a bivariate normal distribution. Is it BVN or BNV? Bivariate normal distribution. Okay, bivariate distribution, like that. So this is saying this is just a bivariate distribution. But if you can write it as a combination of some two independent normals, then you can conclude that it's a bivariate normal distribution. Similarly, not similarly, but also another case where if you already know that this is a bivariate normal distribution, right? Then you can write this as a combination of two independent standard normals. Okay, I hope that makes sense. Cool, yeah, makes sense. So let's go back to the question. The question is saying we're given the bivariate distribution. In this case, we're told that it's a bivariate normal distribution. So already the fact that we know that this is a bivariate normal distribution, already this tells us that you can actually write this here as a combination of two independent standard normals, right? But you know, that's not very important at this stage. So you're given this here, and the first question is asking us to find the probability that 7y less than minus 0.5, given that x is equal to 9 minus y, right? And then they even say that write your answer in terms of this here. We know that this is a CDF of a standard normal. So this is the information that you are given here. And then the question is asking us to find the probability of that statement that you are given there. So the first thing that you will always do, whatever we're going to do, our answer, right, whenever you're dealing with a bivariate case, especially if you want to find probabilities and expectation, this is a property that we will always use, right? The one where we say that a vector W, which has got U and V, right, is equal, it's got a bivariate normal distribution of A mu plus B and A that A transpose, right? This is a property we'll always use when you're dealing with a probability question and an expectation question under the bivariate normal distribution, right? And part of us answering the question is us determining what A is in these cases, right? Because in everything else will be given. This here is given, and then this here is given. As for a B, there isn't any b here, because this b is in a case where you've got 7y plus something, but nothing to worry about. I'll find an example which has this, and then we can see how you use this b. But what we are mainly focused on here is our a, because like I said, this here is given, and that is given, which is what we have here and there, right? So now we want to find a. The first thing that you will have to do when you're dealing with a question like this here, you've got your 7y being less than 0.5, given that x is equal to 9 minus y. First thing, on both these sides here, okay, hold on. Okay, property. There's a question about when we use the property. Which property is this again? The one I wrote now in pink, or can I see? Could you please just let me know which property we're talking about? Okay, while I wait for the one on the board. Oh, okay. Always, actually, when we would use that property? Always. The question was, when would we use this property here? This is something you would use always. Why? Because whenever, you will see why we would always use this. Because here we have information about y, x, and y, right? This is a bivariate normal distribution with x and your y's, right? And the reason why I am saying we always use this here, because this here is some transformation, in a way, if I could call it like that, where now we will be dealing with the u and v. So as much as we're given our information in terms of our x and y's, what we want is to transform this here into a problem where we'll be dealing now with the with the random variables u and v. And once we've done that, we will then need to find the distribution of that u and v, and this is what we would use to find that distribution of u and v. Okay, I hope that answers your question. Oh, okay. And then there's also a question here, why would you not need to find a b? And this is because this b will be some, let's see, it should be something like another vector. Let's say 1 and 2. It will be specifically mentioned that maybe, okay, there are hardly questions that are like that. I've only seen one question. I'll try and find it. But the b will be something that if there is that b there, it will be something that will be added on the mean. It will be some other vector which is there, which means after you've multiplied your a and your a and the mu, let's say that you get an answer which is 1 and 1, right? Then you'd have to add that b there, which is might be your 1 and 2, so that you can just get one vector by adding these two here. I think this would be 2 and a 3, something like that. But I think to perfectly explain why we're not using this b here, because this b is just you after getting this part here, then you add some other vector. I would have to find like a proper question which actually has that b for us to then be able to know exactly when to use it. But just to say it again, this is after you've multiplied, you've gotten your a, and you multiply your a and your mu, and then you add the b like that. Cool. I hope that answers the question. But yeah, I'll find a proper example with the b, then you can use it. And also, if maybe another explanation comes in mind while we're doing the question, then I'll go back to it again. Cool. Then the next thing is that, or like I said, we'll always use this here, right? Because we are given a problem in terms of x and your y, but we are going to try and transform this here into a u and v problem instead of your x and the y problem. And the first thing that you would do is that this probability thing that you have here, try to have, so we've got two sides, this side here and the given side. Try to make sure that your x and your y's are on one side of the inequality or equality sign. What I mean is that have this as the probability that 7y is less than minus 0.5. Nothing changes here because already all my variables are on one side, which is just the only y in this case. Given that x, now I have a y on the right-hand side here. So you want to take that y to this side so that you have x plus y just being equal to 9, like that. Okay, so this is now what I have in my question. It was initially this way. I've not really changed anything. All I've done is to let my variables be on one side of the equality side, on both the side, the left-hand side here, and the given side of my equation, if I can call it an equation. And then the next part will be then for you to let this side with the variables, and also this side with the variables on their own. You now name this U and you name this V, right? Because now instead of having two variables on one side, like in this case, it's just fortunate that for this side, we only have something in terms of Y. But the reason why we do this U and V thing is that in a case where there's X plus Y, in this case here, we want it to be something with just one variable. Because remember, our marginals, they only gives us information for X given Y and for F, Y given X, right? This is why we want U and V, because we just want something that's just going to have one random variable instead of having two that side, right? So in this problem now will simply just become a probability of U being less than minus 0.5 given that a V is equal to 9. And this is definitely something that we can work with because this is what we have. These are the marginals that we have there, right? So now we have translated this problem into an X and Y problem into a U and V problem, which only has one random variable on each side and one random variable on each side, instead of having X and Y on both sides and X and Y on also both sides in our questions, except that this question here only just has the Y on one side as it is there. Then the next thing, again, remember, we said we would be using this property here, which needs us to find the matrix A. So now the next part is then for us to find our A. And then our A, you'll find it by saying your UV will be equal to, then you open your bracket. So here, this is what we had initially and translated. It was in terms of our X and Y, again, there's just Y this side here. For you to find the matrix A, all you have to do is to find the coefficients of your X and your Y's in what you had initially before we became to our U and V, right? So this is saying the U and V, the transformation that we have, we're going to write where it's actually coming from, right? Where we're going to be considering the coefficients of our X and your Y's, and always starting with your X coefficient, right? Obviously, in this case, as you can see, we only have a 7Y, which means there is no coefficient of X, which means we're just going to write a 0 there. And then on this side here, the coefficient of Y will be a 1. Then will be a 1. And then, hold on, let's see. Just trying to see where I wrote this. Okay, what did I do wrong here? Oh, okay, no, I see what I was getting confused a little bit. So the next step that we take here is that I will look for the coefficient of X right on top. The coefficient of X in this case here is a 0, and then the coefficient of X in this case here is a 1. Hence, I have a 1 on top there. Then now we're going to consider the coefficient of X in the other case, which is, what am I doing? Sorry. Okay, let's go back again. So what we have is this here, right? And now we want to translate this into the matrix A that we want to find. And the first thing that you would do is to consider this side here, and you want the coefficient of X, which we said there isn't any coefficient of X since there's no X in this. Let's see. Are we allowed to remove random variables across equations like that? 7, should not 1. Yeah, okay, at the 7, 1 there, I made a mistake. Was now we want the coefficient of X, which you said is 0. Then now we also want the coefficient of our Y, which in this case is 7. And then the next thing for this one, the coefficient of X is 1. And the coefficient of Y also in this case here is 1. And you have your X and your Y like that. Where now this matrix that we have here is our matrix A, right? Then I just want to quickly look at this one other question that was in the group. If we are allowed to move random variables across equations like that. Yes, we are allowed. We are allowed to do that. It's still just like algebra in a way where you just have your X equal to 9 minus Y like that. So yes, you are allowed to move them around in this manner where we had a minus Y this side and then we take it to this side and then we have this thing here. But it's still the same thing. If I were to take it back, I will still get back to that minus Y. So you are able to do that, right? Cool. So the next thing now that follows, remember, this is the transformation. We want the distribution of the UV. Because we have this information, and now we've translated into this. And for us to be able to answer this question, we want its distribution, the distribution of UV using this here, right? Because remember, this is saying now that this UV has got a bivariate distribution with these parameters that are given there. And what we would have now is that our UV will now have a bivariate normal distribution, and these are the following parameters. I could write them down one by one, but then that would just be a lot of space, and I feel like it's something that you can use your calculators with. Just get comfortable with using your calculator to simplify the answers here. But the answers that I'm going to write here, I simply got them by saying, in this case here, we have our A multiplied by mu, which is saying that this is our mu, right? So all I would have done here is just to have my 0, my 1, my 1, my 1, and then I multiply this with my mu, which is 1 and a 1, like that, okay? And then the next thing that I would do is the part of the covariance matrix, right? Where I will still take my A, this matrix that we have here, multiply it with the covariance matrix, which is what we were given here, and you multiply this with the transpose of your A matrix. And then the answer that you should get there when you do that, this is something that you can also just verify. You should get the matrix 3, 7, 7, 3, 5, 1, 8, and 5, 1, 8, and 8, 1, like that, right? This is what you should get. You can always verify that, which means this UV that we have has got a bivariate normal distribution of, when you also simplify this, say you would get that this is just a 7 and a 2, and you have your 3, 7, 7, 3, 5, 1, 8, 5, 1, 8, 8, 1, like this. Again, this is something that I probably did not mention earlier on. If you were to look at the structure, of a covariance matrix, right? Covariance matrix, let's say we're dealing with our X and Y again. This is simply just the variance of your X, and then your variance of your Y, like this, and then this here is your covariance of your X and Y, and this is your covariance of your X and Y, like that. Which means that these values that we have here actually mean something. This is your variance of your U, not X. Because remember, our problem was an X and Y problem, but now we've changed it into a U and V problem instead. Which means this here is the variance of your U, this here is also the variance of your V, then this is actually just the covariance of your U and V. Hence, the numbers are the same here. So which is something to always look out for. In a case where you actually get a question like this in the test, when you get your final answer and these two answers are not the same, then you would actually have to redo it, because this is the covariance of X and Y. So it should actually just be the same thing there. Cool. So that's that. Now we've used that property that I said. I hope you've underlined it somewhere up there. The property that I said we would always use it, we've actually now used it, and we end up getting that UV is actually a bivariate normal distribution, and the mean vector is 7, 2, and 3, 7, 7, 3, and we have 5, 1, 8 here, 5, 1, 8, and 3, oh no, not 3, and then 81, like that. So this is now what we have. But remember, our question here was asking for, it was a probability question, which we have translated into being the probability of U being less than minus 0.5, given that our V was equal to 9. And then from this here, we can now use those marginals. Remember, we said that if X and Y are a bivariate normal distribution, then their marginals in that case would be normal distribution. And I'm sure you'd agree that now this U and V there, if I were to write a PDF of U given V, from the information we have, this should give us a normal distribution, a univariate case with a mean of U plus the correlation coefficient of our U and V multiplied by the standard deviation of U divided by the standard deviation of our V multiplied by V minus the mean of V itself multiplied by this variance of U here, right? Multiplied by 1 minus the correlation coefficient of UV squared, like that. Okay, so then you go further. Again, if I can just mention this quickly, it's only when you're looking for a probability, if it's a probability question, that you then just find this whole distribution as it is on its own. But if it was an expectation problem, as you will see when you do part of this question, all you then need is just this part, something that I've already mentioned. But because we're dealing with the probability question now, we actually need to fill in all these blanks here and find a final answer. So our FU given V will now just be a normal distribution of the mean of V. The mean of V in this case here would not be using this here. That's why I say that you would always use this property, which ended up giving us this, because everything that we're going to be filling in now on this distribution now is going to be coming from what you would have gotten there using that other property that you said you would always use, right? And now the mean of U in this case, U is on top. So the mean of U in this case here will be equal to 7 plus the correlation coefficient. Remember, the correlation coefficient says it's equal to the covariance of the two random variables divided by the product of their marginal standard deviations, right? Which in this case, the covariance of our U and V is actually just 518, and you're going to divide this with the standard deviation of U, and the variance of U is that one there. So its standard deviation will be the square root of 3773 multiplied by the standard deviation of V, which is 81 in this case, right? And you multiply this with the standard deviation of U, the one you're interested in, which in this case here will be the square root again of your 3773 divided by the standard deviation of this one, which will be the square root of 18, like that. Cool. And then you're going to multiply this with our V, right? The V is what you're given. Remember, this is FU given a V. So in this case, what we are given is V equal to 9. So you would substitute 9 minus the mean of our V. In this case, we're looking from that there is just a 2, right? And guys, you will just do the same thing and also substitute for that other term there for your variance. And when you do this correctly, and also please do double check it for me as well, this would give you something where you're going to simplify this as 13.395, and you have 460.358, something like that there. You can always just verify this here with the calculator, but basically every other term here, if you were to go with the formula correctly, I don't know if they now give you this on the formula sheet, but in our year they didn't. It was something that you need to make sure that you were comfortable with to produce it again. But if we had this correctly, and this year I'm sure is correct, if you plug in this, you should get an answer which we will use now here. Right? Remember, our question was asking us for the probability of U given minus 0.5 given V is actually just equal to 9, right? And now we'll do this in the way we used to do problems like this in first year, right? Where you're going to use like a standard normal. You're going to standardize it. I mean, this would be the probability of Z being less than 0 minus 0.5, right? Minus the mean that we have here. The mean that we have there, which is 13.95. So we have a minus 13.395 divided by the square root of our variance, which in this case is equal to 460.358, like this, right? So that's how we will end up finding that answer there. And fortunately, in this case here, you don't even have to end up going to your standard tables, because remember, the question was saying you can leave your answer in terms of this here, and you just have minus 0.5 minus 13.395 over square root of 460.358. So in this case here, you are allowed to use to just leave your answer in that manner. But if not, even if you were to leave it here because of the sake of time, because I'm trying to be a mark, but which would be helpful, obviously, you can always then just go this and check this out from your standard tables and get your answer from there. Okay. And in a case where, for example, let's say with the same information that were given initially, let's say now what you were asked for was the expectation, and you were asked for the expectation of let's say 7x plus y, given that x plus y was equal to 1. Okay, in a situation where this was the question that you were given there, you would do it the same way. The way you start the question is the same. You start by naming this thing, these values that you have here on the right, Most cases, then it's just the expectation of something, not an equation on this left side, but there will be an equation. Sometimes that equation will be such that your y could be that other side there. So the first thing you do is to have your variables on one side, like we mentioned earlier on. Then you translate this to be a u and that be a v, so that now what you're just looking for is the expectation of u, and given that your v is equal to 1. And you do the whole process where you're going to use this property that uv as well a bivariate normal distribution of a mu plus b and a covariance matrix a transpose, like that. You do the same thing until you get to this point where you find your conditional PDF of your u and v, right? Which you're saying is for the normal distribution. But the only thing that you want is the first term there. This will not matter. All you'd want is this term. You then just have to find this term. What's on its own there is actually the expectation of u given your v. Okay. Oh, the question is what happened to the v when we're calculating the probability problem? Remember, when we got to this point, right? We went to we considered the distribution of the PDF of f of u given v, right? Which is what we have here. And part of this term, we have the mu of the mean of u, right? Which we have here, and the correlation coefficient, and then this here, and this is multiplied by v. Okay, I'll write this again to make it clear. Then this here, after this, we multiply by v minus the mean of that v, right? And in this case, the v is what we are given, right? Remember, it's u given v. So hence, at this point, I actually have a 9 minus 2. Why? Because the v that we're given here is equal to 9. So where there's that v there, this is where you're going to substitute in what you're given, which is a v, right? And then minus its mean, which is a 2 there. So in the example that I'm talking about of an expectation problem now, where we get the expectation of 7x plus y given x plus y was equal to 1, we are saying we can make this to be an expectation of u given that your v is equal to 1, right? So if we then, when we get to this point, where we're saying f u given v is equal to mu, this is the mean, right? Mu plus the correlation coefficient of u and v multiplied by that, multiplied by this, multiplied by v minus mu v, right? So this v is like, as the question is asking what we did with the v equal to 9, this part here comes into play here, where we have v minus mu of v, right? We would write this v as it is given there, which is 1 multiplied by the mean of v, which would get it from what distribution would have gotten, right? So just to go over it again, that's exactly how we use the v equal to 9 in this problem. On this term here, where it says v minus the mu of v, that's where we substitute the 9 minus the mean of the v, which we would find here on this distribution, because remember v is at the bottom, so the mean of v in this case is 2, so hence we would have a 9 minus 2 in this case, which is what we have in that part of the question there. I hope that answers the question. Cool. Yeah, so guys, that is basically most of the stuff that is important under the bivariate. Oh, there's one other thing. Can I rub what's on the board? Just want to make sure that you guys are still with me. Can I rub what's on the board? Okay, that's the majority. Cool. So one other thing that's important for you to be able to answer under the bivariate case, right, also goes back to the important concept that we just mentioned earlier on, that if px of y is equal to 0, right, which means that the covariance of x and y is equal to 0, then you can conclude that your x and your y are independent, right? Now, one of the questions that you could be asked here is something in this manner, where you're given the covariance of ax plus y and x plus y, like that. Then the question just asks you to find the value of a. Remember, a in this case is just a constant. This a is an element of real numbers. It's a constant. So the question could be find a, right? An element of find a, an element of real numbers, such that
ax plus y and your x plus y are independent. You know, so this question would even come in a nicer way where already you're given a hint, or it's already given in the form that covariance or something, which already tells you that whatever you're going to do, you'll be using properties of covariance. But it could also just come in the form of just find the value of A such that this and that are independent. And remember, for now, for the bivariate case, we did say that if the covariance of the x and y is equal to 0, then you can conclude that these two are independent. So for you to solve a problem like this here, all you have to do is to solve the covariance of ax plus y and x plus y being equal to 0. That's all you have to do. Find the value of a that is going to equate this equal to 0. And you're going to use the properties that we've looked at already, where you're going to have ax and x plus the covariance of y. Sorry, this will be the covariance of your ax and x plus your covariance of your ax plus your y being equal to 0. So you still just use the normal properties that we've been using, and yeah, which is something that I'm sure by now will be easy. And if it's still a little bit of a problem, you can always just go over it to find the value of a. What I wanted to emphasize under this question is that when you're done, was the question like this, it's not a matter of you then just finding what the value of a is. When you're done finding the value of your a, what it's very important that now you go back to this, to knowing that if you were to do some transformation, whatnot, then this way the bivariate normal distribution of a mu plus b, a multiplied by the covariance matrix multiplied by the a transpose, right? And the reason I'm writing this is that, remember now for your a, right? For your a, you would have, let's say you would have your UV. Your UV would have been something like your A, 1 and 1 and 1 and X, Y, like this here. And this is all coming from this. Because remember, I don't want it to be too dodgy. Remember, you've got your X plus Y and you've got your X plus Y, like that. So I'm just using this here to find my A, right? In that, the coefficient of X there is A, then we've got a coefficient of 1, and it's 1 and 1, and you have that like that. So now you have your matrix A, right? This is what I want us to get to. You've got a matrix of A, and then the next thing that you're going to do from there is just that you already found your value of A. Let's say you find your A to be equal to 1/3. So what you need then is just to write that your A is equal to 1/3 and the 1 and the 1 and the 1 and the 1 here. Then you will come back to this and write Bn, and you write what you use this here to find what this answer would be. Multiply your A and your mu vector. And this part, you don't need to write all of it out. You can just write A still. Then this is the important part where you're going to write the variance of u and 0 and 0 and the variance of your v, like that. And the reason why this is important, right? It's because, remember, for us to be able to use this property that we're using here, this is something that's only possible when you're dealing with the bivariate normal distribution, right? And therefore, once you get the answer, you do need to show that the reason you did this is because this all information was coming from some distribution, which is called a bivariate normal distribution, and the covariance is there as 0. So the important thing for you to then, just to go back on it again, you get your answer, you got the value of your A there, right? Then you just have to remember that you use this formula. And if you maybe run out of time and you want to quickly finish, you can even just leave it as it is there. But what's very important is that you're already showing that this is coming from something that is called a bivariate normal distribution, and then there is a variance which is called a covariance of 0 and a 0 there. Hence, we're able to do that. But I guess as well, if time does not allow, you can literally just write it in words. Says that, Lucy, if you were to look at these solutions from past tests or even OTs, whenever you find this value of A or maybe alpha, because you're likely using A or alpha there, you always then hence this funny stuff that you write at the bottom there. But the reason is because it just wants to prove that the reason why you were able to do this or before, whatever you used here, especially the part where you're saying the covariance of that is equal to 0, is because you're coming from a bivariate normal distribution and this covariance there is equal to 0. therefore you did whatever you'd have done there before. Okay, so yeah, not a big deal though, guys. In the worst case, really, you can just do that and just explain that since it's a bivariate normal distribution, we can assume that if the covariance is 0 to 0, then that and that is independent. So then you just solve. Okay, that's about it then. Can I just get a thumbs up to make sure that we are all good with what's happening now? Okay, cool. Let's go to the next part, which is under conditioning. There's still a lot. Okay, conditioning. Okay, cool. So under this here, I'm also just going to quickly browse through it and write some formulas that are important and say things that are important. And the first thing that we will note under this topic, the conditioning, is just the basic thing that we know, definition of conditioning from first year. That you know that the probability of x given b, the probability of x being an element of some b given a is simply just equal to the probability of x being an element of b intersecting with this event a divided by the probability of a. Okay, this is something that's very simple, but it's always very important to know the basics, guys. Like knowing this definition here, there are a lot of problems that Lucy could give you a question, and it could be so complicated that it gives you a hint, and maybe then gives you a hint that no, like expand, or just expand this here. Then this could always be your starting point when you're answering a question. Hence, I just wrote it down that for you, just remember that this is the case. And it also then goes to this point here that if maybe you want the CDF of x given a, right? Remember, a is also some other event, and it could be a in this case. There could be maybe, let's say that x is greater than 1, right? This is just representing some other event. This here is equal to the probability. Is equal to the probability that x is less or equal than x intersecting some a divided by the probability of a again, right? So this is how you would find a CDF. Let's say you want the CDF of x given some other event a. If you want this would be a starting point. That this is simply just going to be the intersection of the definition of a CDF there, intersecting with that divided by what you're conditioning on there. Okay, and straight up from that, I want to quickly just then talk about the conditional expectation. That is the conditional expectation of x given your a, right? And the way you find this here by definition, like we're doing with expectations earlier on, this is simply just going to be you integrating from minus infinity to infinity, and you multiply x, right? Because remember, this is still actually just asking. It's an x problem. Right, it's still wanting the expectation of x, except that now we are given some extra information, and you still multiply by x here, but except that now you're going to be multiplying with the CDF of the PDF of x given a dx, like that. This is obviously in a continuous case. If it was a discrete case, you are going to be summing x multiplied by the PMF of x given that a that you want there, right? But in most cases, you would find that if you're dealing with these situations here of the expectation of x given a, you would find that it's sometimes actually easier for you to use the that Vader method, because using this here means you first, in a case where you're not even given, maybe you're not given this PDF, right? Maybe it's a situation where you first have to find your CDF, your conditional CDF, then find the first derivative to find the PDF, and then finally you can do this here. So in a case where you do not want to do that, you can definitely use the that Vader, right? Obviously, the first condition is that this distribution you're dealing with here is actually greater than 0. It's non-negative. So then the expectation of your x given your a, in this case now, will simply be just from 0 to infinity, 1 minus the conditional CDF of that, and with respect to dx. You then use the that Vader to find your expectation in this case. right? This is the case where maybe, especially in a situation where maybe the first question is asking you to find the CDF. And once you've got the CDF already, if you want the expectation, sure, you can find the first derivative. Sometimes it's actually very easy for you to do that if you're more comfortable with this method. But in a case where you just want to be quick, you can just use your Bivariate method, and then you integrate from 0 to infinity of your survival function. Because remember, this is our survival function, which is just actually x of a, like that. It's just our survival function as it is there. Cool. And the next thing that's important under this is, if you have to show, remember last time we spoke about showing that a CDF is absolutely continuous, right? So in a case where maybe you're asked to show that your fx of a is absolutely continuous, right? This is something that could be asked, that maybe you have to find the CDF of x given a, then you have to show if it's absolutely continuous or not. So the moment that you found the CDF, right? If the question was first asking you to find the CDF of x given a, the moment you got that, then your answer on whether this is absolutely continuous or not, your answer would be yes, right? The moment you get this here, then you can say your answer is yes, and because this is yes, because if your fx of a given a of b minus your fx given a of a is simply just equal to integrating from a to b of your PDF of that x with respect to dx. The only work that you would do in a question like this here is the part that follows, where you then have to write where fx of a x given a is equal to. Then you now have to write what the PDF is in that case. So just to go over it again, you found your CDF. We explained how you find your CDF there. It's just simple definitions. You know that this is the intersection of x being less than x intersecting a divided by the probability of a itself. And somehow you then manage to get the correct, you got the correct answer. Not somehow, but you got the correct answer. And then you now have the CDF of your distribution. If you want the expectation, because remember, the reason why we do all of these things of finding distributions and stuff is because you want more information about that distribution. And now you're then, after finding the CDF, you manage to get the conditional expectation either by multiplying x and the PDF of that, or by simply using your data, and you got that. Then the next follow-up question was asking, or maybe saying, sure, that this is actually absolutely continuous, actually asking if it's absolutely continuous or not. And because you managed to get the CDF there, definitely your answer will be yes, it's absolutely continuous. Why? Because this and that here is simply equal to that, where this is that. So you then have to find, the only work you have to do when showing that something is absolutely continuous is you finding this part here, the conditional PDF of x given a. And just to summarize this part that we're doing here, I just want to quickly talk about, I don't know if I can, this famous example where you actually have to find the expectation of x given that x is greater than y, and that the expectation of x is given x is less than y. I'm not going to do the example because I know you have the solutions and you've done many times, but what I just want to do is just outline a few important things that are that you can pick up from this question here. The first one is obviously that the expectation of x, right, is simply equal to the expectation of x, given that your x is greater than y, multiplied by the probability that x is greater than y, plus the expectation of x, given that x is less than y, multiplied by the probability that your x is less than y. There's actually a lot to learn from this statement here, because this is just that you are dealing with two regions here. You've got a number line, then there's this part where your x is less than y, then there's this part where your y is actually greater than x in that case, right? So this is just basically what's happening here. You're looking for an expectation of x under this one region, and you're multiplying the probability of that region, right? And then you are also doing the same thing here, but then you're saying that all of this together will add up to just the expectation of x. But anyway, that's not the part that I wanted to outline of this question here. What I wanted to outline is that, So we know that the question could be asking us to find the expectation of one of these here, right? But by just finding one and the expectation of x, we can solve and get our final answer. But what I wanted to do was just going back to CDF of the condition or under conditioning. The CDF of x, given that our x is greater than y. I just wanted to quickly talk about that under this example here. So we know that by definition, we said this is equal to the probability of x being less or equal than x intersecting with our x being greater than y divided by the probability of x being greater than y. If we simplify this here is simply just equal to the probability. If you look at this, x is less than x, but x is greater than y. So this just means that our x is between x and this small letter x, like this, and the probability of x being greater than y. And the reason why I'm wasting your time with the question that you have the answers to is just that I wanted to explain this part that follows, that you can easily make a mistake and assume that this part here will now just be equal to f of x at x minus f of x at y divided by the probability that x is greater than y. And I don't mind this part here. My point is that part there. This here is not possible. You cannot do this here, right? I just wanted to make sure that, like, you watch out for something like this when you're writing your test, that when you get to this point, sure, this almost looks right because we do have a definition which tells us that f of b minus f of a is simply just equal to you integrating between a and b of let's see, of a PDF x and y, like that, dx and dy or whatever. But the point is, what am I doing? Fx and dx, like that. So we do have something that is like this, which tells us something like this here, which is just the probability that our x is between a and b. But remember, this a and b's that you're dealing with here, these are numbers, element of the real numbers. So this only works if your y and your x were both element of the real numbers. Like this x here, because remember, this x is a small letter x, but this y is actually a random variable, which means you are not able to do this part, to do that there on the numerator. That's what I just wanted to outline. Whereas then for you to then solve what's on the numerator there, which is the probability that y is less than x, you then have to actually use the formula that if you were to look with some sections before this one, the probability of x and your y being an element of some region there. There's a formula for that where you're going to now end up using your double integrations to find your answer, right? You would have to draw a region, you know, you've got some x there, and this is telling us that y is less than x. So we have a line, and our y is less than x, and we know that that is happening here. You draw this, and you find the probability. You'd have to do a double integration. But again, the reason why I did this for question is just to make sure, remember, whenever you get to a point like this here, and one of them is a random variable like that on the side, like if x was between a small y and a small x, you can do that. F of x at x minus f of x at y, yes. But once one of them is a random variable, then you actually have to do the probability question using, you having you to draw a region first and then doing your double integration. Cool. And yeah, I think that's it about that. Then the next thing that I want to quickly look at is then, because now we've mainly just been focusing on, we've spoken more about the CDF, the conditional CDF. We can also look at the PDFs. We didn't say much about the PDFs, but we did talk about how they exist. And if you have a conditional CDF, for you to find the conditional PDF, you can simply just take the first derivative. Now the next thing is that if you want the conditional PDF of x given your y, right, this is x given y, this is simply equal to you finding the joint of x and y multiplied by that divided by the conditional PMF of what you're given, right? This is again something that's in your notes. And then in a continuous case, if you want this PDF of x given your y, x given y, this will be equal to the joint PDF of your x and y, x dot and f y, which is what you are given. Again, as you can see, guys, this is simple formulas, right? Which makes it very simple to find these conditional distributions. The only hard part of these questions is that in most cases, it will not be this straightforward. It will actually be a matter of you finding first the CDF, right? Which means in most cases, you would have to draw some region. There'll be a region that you are going to have to draw for you to find your joint PDF of X and Y. Or maybe it could be a question where you'll be given information about an X and Y, right? Then they will give you more information about you, about your X being equal to maybe S plus T, and then you get your Y being equal to 2S minus T, something like this. Then they want you to find the PDF of ST, something like this. Then now you need to find your conditional like that, which means as much as this formula looks very easy, there's a lot of work that might actually you would have to do before you can get to apply this formula. And an example is what I just gave you now, where you're given X and your Y, and you have to do that short transformation with the Jacobian, only for you to then find your what? Your joint PDF, right? And then once you find this joint PDF, you then have to find your marginals. Because remember, if you want the joint PD, the conditional of S given T, you want FST divided by FT, like that. Which means you use the Jacobian formula after having met the conditions. Then you have that there. Then you then have to find the marginal of T, which you will find by integrating, right, your joint, but with respect to S, and only then can you then start substituting in the formula there. So again, the formula is easy, but in most cases, you would have gone through a lot for you to actually end up being able to actually then use that formula that you have there. And because in most cases, I've always been very biased in using continuous cases. Now, just to go more on this here, I want to quickly just do a discrete problem. You will find that in most cases, when you come across a discrete problem, it looks hard, but actually the discrete is easy. It's just that most of the times we focus on the continuous case, and then when the discrete question comes, it looks more difficult than it actually is. So here, let's say you're given a PMF of X, and this is equal to X over 3, where your X is running from 1 and just 2. It's just 1 and 2. But I want to make it as simple as possible. And then now you are given a conditional PMF of Y given X, and this here, and let's say you're given that it's got a binomial distribution with X and P being equal to 1 over 4, and Y is running from 0 to X, right? So it's starting from 0 and it ends where X ends. So I can also just write that this is running from 0, 1, and 2. Right? It's very important for you to be able to interpret this. This is very simple anyway, but knowing what the range of your X and your Y is often very important in questions like this. Then, okay, I just want to quickly write this down here. So this PMF, because it's just got a binomial distribution with these parameters, this is actually just X choose Y, 0.25 to the power Y, 0.75, and X minus Y, like that. That's the distribution of that. Nothing fancy. What I've done is just taken the information that I have here as parameters and I substituted into the formula of the binomial distribution, right? Now, the first question could be find the expectation of X, right? This will be two marks that will be free, for example, because you have the PMF of X and then you have the range of X. So finding this here is just a matter of saying X multiplied by the the probabilities at each point, like that. So that one would be easy. Then now you could be asked to find the expectation of Y, right? Also something that should be easy, but in a case where we actually have the marginal distribution of Y. The reason why I'm doing this here again, I just want to play around with these formulas like a conditional of a discrete case and going to your joint, because for you to find this marginal, remember for a discrete case, you do this using a table, right? Where this will be a Y, and then this here, let's say, is our X, and we know our X is running from 1 to 2, as we have here, remember, in the information, and then our Y is running from 0, 1 to 2, like that. And also remember that when you have something like this, the inside of the inside of this table is actually your joint. That's where you have your joint PMF. So whenever you're asked to find a joint PMF of a discrete case, right? In a case where you cannot get it as a formula like that, which is most of the times, it's something that will have you drawing a table with the ranges of your y and your ranges of your x, and then from that you have answers that you have values that you get inside here, and those numbers that you have there are actually the joint PMF of your x and your y, right? So now what we have is this, and like I'm saying now, we need the joints inside here, because once you're done with your joints, when you add them up and you add the numbers down here, you add the numbers down here, the numbers down here, this will actually be the marginal of y at the bottom here. And then this side will be the marginal of x, because you'll be adding the x's there, that will be your marginal of x. And this corner there should always just be equal to a 1. So I'm going to quickly rub here. And so now what I will actually want is just what to put in here, which is just the joint PDF, right? And what I just rubbed there was telling us that the joint of y given x is just going to be equal to, the condition of y given x is going to be the joint divided by the PMF of x in this case, right? Which means that if I want the joint, which is what I want to substitute in there, is this will simply just be equal to that. The joint of y and x will be equal to the conditional multiplied by the marginal of x, right? And once you do that, you find that this is equal to this. This is equal to x choose y 0.2 to the power y 0.75 to the power x minus y multiplied by this here, which we were given as x over 3. And that is the formula of your joint PMF of your x and your y. And all that then follows from that is that these are your x values, these are your y values. So all you need to do now is to substitute these values. What I mean is that for the first part, when our y is 0, and this is when our x is 1, which will be the answer we'll put here. Where there's x, you'll be putting a 1. So I have a 1 here, I have a 0, 0, I have a 1, 0, and just that. That's just simple stuff substituting in. And you'll find that you can always just double check this here. You should get these values, and 1 over 12, and 1 over 4, and 0, and 1 over 24, like that. So this is the joint distribution. So if the question was just like, what is the joint distribution of your x and y, right? So you could have just done this here and left and have a mathematical formula for the joint, but always then leave it like this in a table, because most of the time, like I've said already, and I'm repeating myself, when you have to find the joint distribution of in a discrete case of x and y, this is what you want to always end up with in the end. Now you add down here so that you end up with a 5 over 8. Then here you have 1 over 3. Then here you're going to have 1 over 24. This way you're going to have 1 over 3. Then you have 2 over 3. And to always confirm if your answer is correct, add them up, right? Add up here and there. It will always just give you 1 there at the corner, like that, right? And remember the question there, just to go back to what the question was asking us for, was the expectation of y. Now we have the marginal of y. Because remember, when you add this up here, these are your y values, and then what you have here is your marginal of y. Which means if I were to write it down, my marginal of y will now be equal to, my margin of y will be equal to 5 over 8. This is 5 over 8 when my x is equal to 0, when my y is equal to 0. My y is equal to 0, and I will have 1 over 3 when my y is equal to 1, and I have 1 over 24 when my y is equal to 2. Because remember, the range of y is from 0 to 2, and this is exactly what we have. Therefore, finding the expectation, I'm going to wrap this now, finding the expectation of y will just become easy as we're finding the expectation of x there by simply saying this is just the summation of y multiplied by the probabilities at each point, which means I'm going to say 5 over 8 times 0 plus 1 over 3 times 1 plus 1 over 24 times 2. And that there would give me my the expectation of y. So yeah, that's basically it. The point of this example was just obviously to outline how the joint PMF of x and y looks like as table form, and also to show you how when you're given the conditional PMF, it's one way that I've noticed they like asking such a question under the discrete case when you want to look at conditionals, that they will give you maybe this here in a mathematical form. Then you have to play around with the fact that you'll be given one marginal, play around with it to get your join. Then you can translate this into that. Then from there, whatever question they can ask you about the expectations or even the probabilities should be quite easy from there, right? Because what this means is that even if they ask you for the joint, let's say they say what is P or XY, then they write 1 and 1 like that. Then now that's just a matter of you locating from your table. Then that will become just, let's say that will just become this number there. That's over 12 there. Cool. And another thing that's also important, I don't remember what test it is, or if it was in my year or in 2018, but if you come across it, they can even just define maybe X minus Y, right? X minus Y. The difference between, let me rather just have Y minus X. Y minus X in this case. They can define another variable, which is Y minus X. That is the difference between that. Then they can even ask you maybe to say then, what is the probability? Maybe this is, let's call this Z. What's the probability that this is equal to Z? That Z is equal to maybe 0, right? And this probability, Z will only be equal to 0 if your X and Y are the same, right? What I mean is that if, for example, when you've got 1 and 1, that means 1 minus 1 will give you what? Will give you a 0. And if you've got 2 and 2, you've got 2 and 2, then you equal to 0. And you've got, okay, there's no 0 and 0. So in this case, Z will only be equal to 0 if you've got 1 and 1. So that means for you to answer this probability that Z is equal to 0, you just have to consider your your joint of Y and X when your Y and your X are equal to 1 plus the probability of your Y, X, and 2, 2, which means then you are just going to be adding 1 over 12 plus, when it's 2, 2, 2, 2, this will be 1 over 24 plus 1 over 24. Cool. So that's basically, most sense, the only thing, because Lucy can always surprise you and come with another question that she can ask you from this. But from what I've seen so far, this is mainly what she could ask you if you was to deal with a discrete case. Obviously, with the continuous case, it will be what I spoke about earlier on, where for you to do all this stuff here, you'll be given some region, you find the joint, you have to find your marginal by integrating with respect to the other and whatnot. But in a discrete case, this is all about it that I can say about this case. Then I want us to just quickly go through a few more notes, then we can take like a short 5 minutes break. So we can like drink water, like I'm literally thirsty from the screaming, but cool. Then the next thing that we're going to look at is, not that it's anything new, we are still just continuing under this section here, the law of total probability, where we have that the probability of A, this is actually very important, guys. Like the more you use this formula and later on you realize that you get to a point where there isn't any probability problem you cannot answer, especially using this here. The probability of A is going to be equal to you integrating the probability of A given Y is equal to A multiplied by the PDF of Y with respect to Y. Or if it's a discrete case, you sum the probability of A divided by Y is equal to Y multiplied by the PMF of Y. Now, I just wanted to quickly note this here, that whether you are going to, obviously, in theory, you can easily just say, you do this when it's a continuous case and you do this with when it's a discrete case. But what determines whether you are going to integrate more or sum is the distribution of what you are conditioning on, right? In this case here, we are conditioning on Y and we are conditioning on Y in that case, which this tells us that Y in this case is actually a continuous random variable. And then in this case here, Y is discrete. So it can happen that you'll be given 2 random variables. This is just an example, right? It's an example that maybe you've got a random variable X, you've got a random variable X, and now you've got also a Y, random variable Y. Let's say it has got a geometric series distribution. Therefore, f of Y, P of Y, like this, is just equal to QYP, right? And then maybe I ask you to then find the CDF of Y, right? Remember the CDF of y, of x, the CDF of x. Don't worry about this example, guys. I'm just trying to emphasize the point where I was saying whether you integrate or sum, this will depend on what you're going to condition on, right? So if I want the CDF of x, by definition, we know that this is equal to the expectation of the probability of x being less or equal to x. Obviously, when you want to find the CDF of a random variable, guys, you don't need to use this method and worry yourself, but you definitely can find the CDF of x using this here, because this is the probability that x is less or equal than x. And if I were to use that method there, this means that this x less or equal than x is what my A is in that case. Which means for me to find my CDF, I can find this by saying that this is equal to, I want to condition on y now, right? But my y is a geometric distribution, which means it's discrete. So that because it's discrete, it means I'm going to use summation. Why? Because like I said, this is determined on what you're going to condition on, right? So therefore, when I want to find the CDF of my x here, this will simply just be equal to the summation, right, with respect to y, right? So if my y is moving from 0, 1, 2 to infinity, this will be my y equal to 0 all the way to infinity of the probability of my x being less or equal than x, given my y is equal to y multiplied by a PMF of y, right? The PMF of y, which in this case is just my QY P, like that. In a nice scenario, this could just be, okay, this will be a bit difficult to then find it. But again, we're not trying to answer this question. The point was just that whether you're going to sum or integrate will be mainly determined on whether what you're conditioning on, which is the y here, is it continuous or is it discrete? Cool. Then, yeah, I want to just give you a quick example on how this kind of question is asked in a test, right? And this is it's mainly asked as follows: that you could be given, let's say, it's an example, and the best I will actually advise you to go and check the test 1, 2018, right? On your resources. This was my test, and I feel like it mainly, from what I remember, it mainly explains exactly how this kind of question is usually asked in a test, right? And there, I guess that's why I'm a bit biased, and I gave this example of my S minus T and whatnot. It's from back then, and we got to a point where we found your marginals of your S and your T, and now there was a question which was asking for the probability that 2S is less than S given S is equal to S, right? So there's a lot of information that was given there, your X and your Y, and you had to find the marginals, your joint of S and T. There was even a conditional question. Actually, it's TS. There was a conditional question of T given S and blah, 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 and stuff. Then there was a question which was asking for the probability of 2T being less than S, given that S is equal to S, like that. Then obviously here, you have to use that formula. You can always just go back and check it, that your X and Y is an element of S, right? You have to use that formula. Basically, what you will have to do there was T and S were independent in the question, if I'm not mistaken. If they were not, I'm going to assume independence there, so that this says that's the probability of my 2T being less than small letter s now, right? Because there's this condition, but now I'm going to use the condition, then this big letter S now becomes small letter s, and that just disappears. Now, this is just a problem of me drawing my region like that. Then I'll have my S here, and my T going this way there. And yeah, you have to draw a line and do that whole region thing and find an answer. Suppose the answer that you get there is half, as you would get in the question if you were to do it, test 1, 2018, right? You get the answer. This would be like part A of the question. Then part B would then ask you to find the probability of 2T being less than S. Right? This almost looks like the same thing, because now initially we're looking for the probability that 2T is less than S given that, and then this here is just there's no condition there, it's an unconditional problem. And the reason why I'm going through this example is for you to see how we use this whole probability of A being equal to that, probability of A given Y is equal to Y multiplied by that, right? Because if you can already, in a case on Tuesday, when you get a question like this, and the first part of it, there's a condition like that, and now what you want is this. Already, you try and connect the dots there. That what you want is the probability of A, which in this case is simply this here, what you have. This is now A. This is the event A that we want, the probability of A. And we know that for us to find this, we are going to, depending on what Y is, we're going to integrate or sum a conditional of what we want there, conditioning it on something else that we have, right? And in this case, what you're going to condition on will always be determined from here, because we want the probability of T, right? Because this is more about T being less than S. So the fact that you've got a T here already should tell you that since you've got this one S that you have information about S, so you are safe to condition whatever you're going to do on this S that you have there, right? And as you can see, initially on A, we did a problem where we're finding an A, but conditioned on what? On some random variable S as well. So this then tells that you are then safe to then assume that, to say that this probability, which I said this part is now our A, but because S in this example, when you do the question again, when you go through it, this S here is a continuous random variable. So I will also be integrating from 0 to infinity, because I'm not sure, I don't know what the bound, but let's assume S is greater than 0. So this is us integrating what? The condition of A given Y, but in this case, we'll be integrating the probability of 2T being less than AS given that S is equal to S, like that. And what do we multiply it with? We'll now multiply it with the PDF of S, and this is all done with respect to S. And the nice thing about this, this example, right, especially in a test where the previous question, where we had to find this term here was a constant, right? What you must always do, okay, this is important, I'll write it down as a trick. So what we were doing actually ends up just being the probability of 2S being S, and we say this is us integrating from 0 to infinity of the probability of 2T being less than S, given that S is equal to S multiplied by the PDF of S ds, like that, right? So the nice thing about the questions, there's a question. Give me a second. Could you find B by finding the expectation of the conditional? Could you find B by finding the expectation of the conditional? Oh, the question is, could you find B? This is what we want, right? By finding, could you find B by finding the conditional expectation of the conditional probability above? Yes, you can. This is basically it. If you look at, if you think about it, this is exactly what we are looking for, because the question is asking if you can find this by finding the conditional expectation of the conditional probability. This is the conditional probability. And remember, when you're looking for expectation, you're going to integrate x multiplied by f of x, like that, right? So this is basically what we are just doing there. This is us finding the expectation. Just that instead of me writing the expectation of the conditional probability, what I've just done is to use that definition. This is basically the definition that if you were to go back to your notes, you and look at this properly. This here, that the probability of A is equal to the integrating probability of A given Y is equal to Y multiplied by f of Y. You would find that us doing this and multiplying with the density like that there with respect to Y, this is actually an expectation problem. But then the reason why I didn't want to talk about that, I didn't want to put like too many concepts at once. But yes, the question, to answer the question again, this you can actually answer this question by finding the expectation of the conditional probability. And when you do that, then you get to this point, you write it down out like this, and you have this part here multiplied by the marginal PDF like that. And fortunately, in this question, in my test, the answer there was 0.5. And I hope if you get a question like this, you also get a constant there, an answer on A, that your answer for part A was equal to 0.5, or some A, a constant. Why? The reason why that it would be nice is because then this will simply be equal to, since it's a constant and independent of S, you can take your half out and you'll be left with integrating Fs like this with respect to S. But remember, one of the properties about integration and random variables is that when you integrate the PDF of a random variable on its interval, this will just be equal to 1. So the answer will also be equal to 1. But in some cases, you find that maybe this here is not just a constant. For example, not that I'm going to go into it, but if you to look at the question, I think in the mock test, there is a part where you can use this here, and I don't think the answer that you get there is a what you call this is a constant. So you could actually end up getting, let's say this is just something random, and maybe you get that this is actually equal to 2x plus 1, and maybe what you had conditioned on there was a geometric x as well, which will gave you q to the x times p. You could end up having something like this here, but then you have to play around and actually just use your x is moving from 0 to infinity, and just do the maths there. Check out everything that's independent of your x, which is your p and the q, and you have your x being equal to 0 to infinity. What's left is 2q to the power 2x multiplied by q to the x, like that. Then you just play around with it, and then that's just maths there. The point is just that to make life easier for yourself, just pray or just hope that this part here will be a constant in the previous case. But anyway, always expect the worst. So that is, expect that you might get something here that is not a constant, and then anyway, it will be basic integration. It will be just integration. You're going to get something here, most probably in terms of s as well. Then you're going to combine them together with the PDF, and then you're going to integrate. It could get as complicated as having to now starting to be able to recognize what you call this, recognizing gamma distributions and beta distributions. But the point is, it's doable. And then as long as you understand the property, that's a great starting point. And I'm sure you'll be able to work something out from there. And the time is 5 o'clock exactly. What do you guys say? We take a 5-minute break and then be back and quickly finish up MGFs and what's remaining. Is that okay? Can I just get a reaction? 5-minute break? Cool. Awesome. So let's quickly have a 5-minute break. 5 past. It's 4 minutes left now. 5 minutes past 5. Let's be back.
So, are you guys ready for us to continue? Can I get a reaction that we are ready to continue? Okay, awesome. Cool. So now we're just going to quickly look at PGFs and FGFs and PGFs for starters, right? And by definition, we know that an MGF is defined as follows: the expectation of t equal to x, or if you were to find it manually, this will be equal to us integrating this here multiplied by the PGF of our x, right? And obviously, this is just coming from the law of the uncontested decision again, because we have information about some x random variable there, but now we want to find the expectation of this other function g of x, which is in terms of our x, like that. And one thing to also note is that if you have got your MGF, take the first derivative and let your t equal to 0. This will give you the expectation of your x. Similarly, if you've got your MGF, take the derivative twice, let your t equal to 0. This will give you the expectation of your x squared, right? Which this on its own actually proves the importance of MGFs, right? In the sense that you can also use this to find the variances of the variance and other properties of your random variable, right? Because remember, if you wanted the variance of x, this is simply just equal to the expectation of your x squared minus the expectation of x. So if you had an MGF and you wanted to find this, if you had it and you got this term and you got this here, you can simply then just substitute into this formula of variance and you have your variance of your x. Then one other important property about MGF is that if the MGF of x is equal to the MGF of y, then it goes both ways, that the distribution of x is equal to the distribution of y. What this statement is simply telling us is that if maybe you want to prove, let's say you want to prove that x has got an exponential distribution, right, with some parameter lambda, it's good enough for you to just show that, because you can easily find the MGF of an exponential distribution on your formula sheet. So for you to show that this random variable x has got an exponential distribution, you can just show that the MGF of x is the same as the MGF of an exponential on your formula sheet. Okay, this is something that I'm sure by now everyone is comfortable with, but just to go over it again, if you want to show, maybe a person is asking you that, prove that the CDF of x is an exponential distribution, or maybe the question is just asking you for the CDF, or showing that it's exponential. All you have to do there is to find the MGF and then relate that MGF to the MGF of an exponential distribution, which you would find on your formula sheet. Then the next thing that's also important is that the same way that the expectation of x is equal to the expectation of the expectation of x given y. I'm sure you might feel like we skipped this concept under conditioning, but we're still going to get back to it. I want to try and combine it together with that whole hen and chicken or cars and whatnot. So that's when we're going to talk about this conditional expectation problem. But anyway, because this is possible, then you can also say that the MGF of x, right, which is equal to the expectation of e to the power xt as we defined, this can also be written just as the expectation of e to the power tx given some random variable, let's say y, like that. This is also something that's possible for us to do. And again, it's something that you even use with, for example, your PGFs, when you're dealing with that whole hen and chicken or cars, some of them turning left or right problem, which you're going to look at very soon. Cool. And the next thing that's important are PGFs. It's all just under our generating functions. Now, PGF is that what we know is that by definition,
the PGF of X is equal to the expectation of S over X. And manually, this is equal to K from 0 to infinity of S to the K and PK multiplied by K. It's very important that you understand both these formulas of PGF and also both of your MGF, right? Because it's very easy to easily rely on this formula and that formula. But there comes cases where you may not be able to use this formula. These formulas here are mainly usable when you are given some random variable X and you put information about it, and now you're given another variable Y equal to X plus Y plus 1 or something like that, which gives you a formula which you can put up here and also here, and then you can break down. But in most cases, not most cases, but in a case where there isn't any transformation that's happening, but instead we're just talking about another variable X which is running, and then maybe you're given the PMF of that or the PDF of that in this other case there. This is the formula you want to use if you're just given the PMF and the range, and there isn't any transformation that's happening. By that I mean there isn't information about a random variable, then you're told about another one which is given in the form as a function of the other one that you're given. Even here as well, you use this one if you're given maybe a range and the PDF of your X random variable. That's the way you usually use them. But the important thing is that just understand both of the formulas there, because you would always then just check which one will work best in whatever problem that should be dealing with at the moment. And the next thing that's important as well under the PGF, the same way that if you wanted the expectation of X and the expectation of X under the MGFs, you could just find the MGF, take the derivative, and let it equal to 0. For a PGF, you can just take, having the PGF, take the first derivative, and let your S equal to 1, then that will give you the expectation of X. The main difference now is that when you take the second derivative of your PGF, right, and you let your S equal to 1, this now gives you the expectation of your X multiplied by X minus 1, like that. Which means if you wanted to find the variant of X and be using these properties of that, there's a question I just want to quickly check. Could you write the summation formula more clearly? Oh, okay. I'll write it down now. This I'm assuming is this one here. This is equal to the summation from K equal to 0 to infinity, and this is S to the K and probability of K and K, like that. I think that's the question. I hope it is. But yeah, this is important. And the reason why I'm outlining this, the reason is because it's from personal experience where I got used to one formula, but now there was a time when I could not use it, and then I didn't probably remember the one. But yeah, it's just important for you to remember both of these formulas as they are. So as I was saying now, when you want the variance for your X now, if you're using the probability generating function, this will now just be equal to the expectation of X minus 1, right, plus the expectation of X minus the expectation of X all squared, like that. So now whenever you want to find the variance, you have to add that term. It's unlike with the PGF problem where the variance of your X, I'm not sure if I wrote the correct formula there, was just equal to this here squared minus the expectation of X, but all squared, like that, right? Where this just came from your MGF, right? But first derivative at 0, and then second at 0, and then this is just 1 at 0, that part. And where this part here is the one where you find your PGF derivative twice, and you let your S be equal to 1. Cool. And then another important fact under PGFs is that, remember, this one is a probability generating function. So we are also able to find probabilities using this this generating function. And the probability that X is equal to R, right? This is the probability that your X is equal to R. It's simply equal to you having your PGF, and you differentiate it R times, you let your X equal to 0, and you divide by R factorial. This is the only time when you substitute as 0 on your probability generating function. Otherwise, when you're finding moments and whatnot, you always substitute 1. But when you're finding a probability, That is when you actually then say this is equal to your PGF. If you want the probability, like if you, I'm sorry, I'm going to refer to test 2 because the closest thing that I remember of some of these questions. I remember there was a probability that x is equal to 2. This means you will take the derivative of the second derivative of your PGF, right? So this is a 2 there, and you let your s equal to 0, and you divide by 2 factorial when you want probabilities. Cool. And similarly with an MGF, we know that if the PGF of x is the same as the PGF of y, then this goes both ways, that then the PMF of x is the same as the PMF of your y, like that. I don't know if you've noticed yet by now, you would say that when you're dealing with the PGF, this actually, I would say always, but normally you would find this is the discrete case. This happens with discrete random variables, because remember, even the definition, we are summing along some numbers, sk, and the probability of those of x being equal to x at some point. Right? So this is a discrete case, hence unlike the MGF where I wrote the PDF being equal to the of x being equal to the PDF of y. Here we're dealing with PMF, right? So if you want to show that some random variable x has got a Poisson distribution, is good enough for you to find the probability generating function of your random variable x and show that it's actually the same as the probability generating function of a Poisson distribution, which again you would find on your formula sheet. Cool. Then another thing which is quite very important, I'm not sure if it's on your formula sheet, but this is also very important, the relationships. Right? The relationships between PGFs and the MGFs. There's no need for you to be able to prove this here, but so I'll just write the final result that if you want a probability generating function, a moment generating function, right, of x, and you already have the PGF, all you have to do in your PGF, substitute e to the power t wherever there's an s, right? Because remember here you would have had g of s like that. Wherever there is the s there, you're going to be substituting e to the power t. And the other way, going backwards, if you want your probability generating function and you have your MGF, all you have to do is to go to your MGF, and where there is t, you're going to be substituting ln s, like that. That's one of the things that are very important under that. And something else that's important, and you know, one thing you need to know is that I know with Melusi, with CAT tests and tutorials, everything is just so difficult and whatnot. But when it comes to TM testing, especially in the exam, test is still very hard. But in tests, is this in exam? It's also these little things there that really matter. Just to know that when you want to change this to that, because maybe it's going to give information about X, right? But you can't find probabilities with that, and you want to find the probability that maybe your x is equal to 3, and it gives you the MGF. The fact that you have the MGF, it means you're able to find your PGF, right? And it means you're able to find your PGF, and once you have your PGF there, you can now then use that the probability that x is equal to 3 will just mean that you should take what? Take the derivative 3 times of your function, and then s is equal to 0 and 3 factorial. So it's just these things here that may look like they don't really matter, but in fact they do make a big difference. And the next thing now for a joint cases, for this was in a univariate case, obviously. Now, if you want an MGF of your x and your x, y, now we have s here and we have a t. This will be the expectation of e to the sx plus t to the y, like that. And this is a definition in the books again, and you would know that if you want the marginal, of x, the marginal MGF of x, and x is corresponding to s, or even s here, this is simply going to your MGF of your x and your y, but now where there's s, you have your s, but where there's a t, you're going to have a 0, right? Because remember with an MGF, we substitute zeros a lot. And then for your marginal of y, which is corresponding to the t there, this is just your joint x, y, but where there's an s, now you put 0, and where there's t, you keep your t, okay? And another thing that's important is that when your x and your y are independent, then this goes both ways, that the MGF of your x and y, st here, is simply just equal to the product of the marginal MGFs, like that. And I'm quickly going to run into PGFs, the join for PGFs as well, that by definition, gxy st like that. This will just be the expectation of now f to the x and t to the y, and our t to the y like that. And also for us to find the marginals, the marginal PGF of x will now just be us going back to our joint, right? But instead of now putting a 0 where there's a t, we will now be putting a 1. For the marginal of y, this will be equal to gx of y. Instead of putting a 0 where there's t, like we did here for an MGF, we'll be putting a 1 here, and then we have a t. Same concept again, that if your x and your y are independent, right? I'm only writing this down here because I don't want to assume stuff, but I think by now you guys know that if x and your y are independent as well, then you can conclude going both ways that the PGF of x and y is simply just going to be the product of the two marginal PGFs. Also important translation is that if you want the PGF of your x and y, this is simply just equal to you going to the MGF of x and y, and where there's s, you put ln s, then you put ln t there. Same way, the other way around, this will be equal to gxy and e to the s and e to the t. Cool. Basic stuff, but again, very important. And I just want you to try and go back to these small properties there. Make sure you understand them. Check if they're on your formula sheet, and so that you know that you don't have to like memorize them. But if they're not on the formula sheet, please just do memorize them, because they are actually very, very important, because you would then get possible questions like this. These are the kind of questions that you could get like in an exam. This was like an exam question. It's not an exam question where you're given that for example, your x was discrete. Your x is discrete, and you're given your x and your y are both discrete. Then you're given the MGF of x and y, right? This is an example. You're given an MGF of x and y, and this is given as e to the power 2 e to the s plus 5 e to the t minus 7, right? And the question was asking for the MGF, the PGF of x on its own. Okay, I'm not going to. Okay. Okay, you got the formula. Cool. So the question is, the question was asking you to find the PGF of x. I will not do this example. I'm just quickly going to talk through it, because there's one that I want us to do, which talks about the same information anyway. So here, for you to find the PGF of x, right? There are two options that you can do. Either you can find the marginal MGF of x from that, because now we know how to do translation first. We know how to move from the joint MGF of x and y to the marginal of our x. And then when you have that there, we also know how to move from an MGF to a PGF. Then you can move from that to simply that, which is what you want as the answer, right? That's one way to do it. Or from there straight, you can move from the joint MGF of x and y to the joint PGF of your x and y, right? Because we know how to move from an MGF to a PGF like that. Because if you can just go back to the notes we wrote now, we know how to do that. And then from there, you can then move to finding your marginal PGF of your x. So there are two ways in which you can answer this kind of questions there. Either straight from there, you find your marginals of your MGFs, then from that, you just go to that one straight, or you can just first change it to a PGF, kind of a problem. Then there's this one quick one that I want us to quickly look at as well, where we'll be given that, I'm so sorry that I might be moving faster now, so that like I'm trying to make time, because I know some others do not appreciate going over time. If we say 3 hours, you should just end in 3 hours. But I want to try and cover everything. And suppose we're given that the MGF of x was equal to 4 over 5 plus 1 over 5 and e to the power t or to the power 3, right? And our x is moving from 0, 1, 2, going onwards there. And suppose the question was saying, find the probability that x is less than 3, right? First question, find the probability that x is less than 3. Obviously, guys, this is stats, and I'm sure now you guys have done a lot of stuff on finding probabilities. There are definitely more ways to find the probability of X being less than 3 here. But since we're under this topic here, I want us to try to use what we know about MGFs and PGFs. So the first thing, we already know that we don't know anything that relates probabilities to a moment generating function, because as it says, it's a moment generating function. So when you want stuff like variance and whatnot, ketosis, when you're doing ketosis, skewness problems, that's when you are more concerned with an MGF. But now what we want is a probability. And as it says in the name, that means we would need a probability generating function, right? So from this one there, we want to find our probability generating function of X, which we know is simply just equal to the MGF of X, but where there's a T, we're going to be substituting in what? Ln X. And if you were to follow that, this formula here of moving from that to getting out of ourselves a PGF, you would find that the answer that you would get would be now that your PGF of your X here is simply equal to 4/5 plus 1/5 e to the power ln s or to the power 3. And your final answer will just be, this is 4/5 plus 1/5 s all to the power 3. But remember, what we wanted there was the probability that this X is less than 3. And again, remember, with the PGFs, when we deal with discrete cases, right? And we know our X is moving, our X is simply just moving from 0, 1, 0, 1, 2, going onwards to infinity. And from that, this simply just tells us that the probability that X is less than 3, this is still just the probability that X is less or equal than 2, right? Which is the probability that our X is equal to 0 plus the probability that our X is equal to 1 plus finally the probability that X is equal to 2, like that. And once we have something like this here, this becomes easy to find these probabilities. Why? Because we know that the probability that X is equal to R is simply us taking the derivative of R times of our PGF and letting our S equal to 0 divided by R factorial. Which means for the first part, for example, you're not going to take any derivative. You're just going to take your PGF as it is, your G of X, right? But let your S be equal to 0, divide this by 0 factorial. Plus, you're going to take the first derivative, right? Let your S equal to 0 divided by 1 factorial. Plus, take this here twice, S equal to 0 and divided by 2 factorial, right? And because this is just labor intensive, as you can see, you're going to be taking derivatives. The highest reasonably that you should go if you ask you this question, like, okay, from experience, it's just 2. That was the highest that you would do that. Because anyway, now that will just be testing your differentiating skills, whereas that will not be necessary. So yeah, 2 should be the most that you would have to take the derivative of that. Another question that you can possibly get that I saw somewhere is, oh, no, that was it. The question there was asking for the probability that X is less than 3, and you translated into that kind of a problem. And if obviously they then asks you from there, the question did have now find the variance of X. Now we know how to find the variance of X. Because by now you'd have taken the second derivative already, which means we have this term. The expectation of X, X minus 1 is there already. And we've taken this one as well, except that you need to remember that you were evaluating this at S equal to 0. But here, this is actually GG twice, but at S equal to 1. So when they want the variance, anyway, we've spoken about the variance of X, and then you find that, then you also need to find your expectation of X, then you just work around from there. And I think it should be pretty simple. Then this other example that I wanted to talk about is the same thing. You have your joint PGF of your X and Y, like this, S and T, and then they will ask you now for the probability that XY is equal to 0. Initially, the questions below there were asking you to find GX, then the other one is asking you for you to find your GY. Now, the probability that XY is equal to 0, that is the probability of X times Y being equal to 0, X times Y, oh, what am I doing? This is the probability that XY is equal to 0, like this, okay? which means that this is actually the probability that either x is equal to 0 or the probability that y is equal to 0. I guess obviously then there's another potential of them being both equal to 0, but I don't think that term is important in this case. But please just to verify that, because this is something that I just thought could be an important thing, but I'm definitely sure about these two terms here. This means that x is equal to 0 or your y is equal to 0, right? And then finding this here does not even require us even taking any derivatives, because this is just 0. So it's something where, like here, where you just have to say g of x, right? And let your s equal to 0 divided by your 0 factorial. So yeah, this here is also something that seems quite important. Cool. And then I want us to quickly move to characteristic functions. Characteristic functions. So now the characteristic functions, they're a little bit, not a little bit, but they come from the concept of MGFs, right? Because you will find that it's not always the case that you'll be able to find the MGF of all random variables, right? For example, if you consider the Cauchy distribution, right, which its PDF is simply just equal to 1 over pi over 1 plus x squared, right, where x is an element of real numbers. If you were to try to find the MGF of this here, right, you can even try it on your own by using the definition as infinity to infinity, right, because fx is running from minus infinity to infinity. This will be us integrating e to the power sx multiplied by 1 over that over 1 plus x squared dx. If you want this, you can verify it, and you find that the answer that you get there is actually infinity, right? So the fact that it's infinity, this means that this MGF does not exist. So in cases where your MGF does not exist, like this here, then you consider like now finding what characteristic function, because you still want to get, suppose you want to get more information about the random variable, you want to get your variance and your whatnot, and your first alternative is like, you know what, I want to use an MGF, but then you find that you cannot use an MGF. Then the next thing that you'd want to use then is maybe then the characteristic function. That's how then you can define your characteristic function. I don't know if I'm drawing this correctly, but yeah, this is supposed to be the characteristic function symbol, but yeah, it's something like that. And then this by definition is the expectation of EITX, like that, right? Where this I squared, this I is simply just equal to the square root of minus 1, okay? And I want to write this relationship here. Then there's a relationship which says that the characteristic function of x is actually, by definition, we know that it's equal to the expectation of ITX, right? But this here, if we were to look at it properly, because we have this IT and x, this is the same as the MGF of x, but evaluated at IT, right? But the condition for this to be possible is only if the MGF of x, is less than infinity. That is, if it exists. In a case where you've got a Cauchy distribution like this here, we cannot use this relationship which says the characteristic function, in case you can see properly here, the characteristic function of t is equal to the MGF of x evaluated at IT. You cannot use this relationship within the Cauchy distribution case, because the condition to this here is that the MGF of x is less than infinity, which means that it actually exists. That's the condition for us to use that. Then the next thing that's important under characteristic function, this is very important, is that if you've got a characteristic function and you take its derivative r times, and you let your t be equal to 0, this is equal to I to the power r expectation of x to the power r, like that. Which means if you want your rth moment, right? If you want an rth moment, this means if you want your rth moment, the expectation of r, like this is simply just equal to 1 over I to the r, 1 over I to the r, and multiplied by the characteristic function, the derivative r times, and your t being equal to 0. So obviously now from here, we can just know that if maybe the same way I was saying, you wanted to find information about x using an MGF, that is find your mean, find your variance and whatnot, but the MTF does not exist, and now your alternative is for you to use your characteristic function, which means if you wanted the expectation of x, right? That is, your r is equal to 1 in this case. This is simply just equal to 1 over r, and you're going to take the first derivative of your characteristic function and relation t equal to 0. If you wanted the expectation of x squared, like this is equal to 1, or this is not r, I mean, sorry, this is I. This is 1 over I squared, characteristic function, the second derivative, and letter t being equal to 0. In the second line, what is the line next to r? The second line. Okay, this is the second. Which one is the second line? Oh yes. Okay, I'm hoping this is it. This is I to the r, and that is I to the power r being equal to that. Yes, I don't think I made a mistake there. Yeah, this is I to the power r expectation of that. Cool, awesome. And then the next thing that follows, my point now was that, like, if you want to find this and that, you can find them in this manner, which means from there you are definitely able to find your variance of x. If you wanted to find the variance of x using characteristic function. So this means now at this point, being able to find variance, being able to find your mean and arc moments and whatnot, there are so many ways that you'll be able to do it. You just need to find one which you will find more comfortable. And the same way as we found with the MTFs and our PGFs, that if the characteristic function of x is the same as the characteristic function of y, it goes both ways, that x, fx, and your fy have got the same distribution there, okay? And another thing that's important is that if your x and your y are independent, then the characteristic function of x and y, right, I'll write ST here, is the same as the product of the marginal characteristics of your x and the characteristic function of your y at t, like that. So this is something that you would expect. Also, if we are dealing with a bivariate case, right, the characteristic function of them together is simply equal to the expectation of e to the power isx plus ity, like that. Cool. So that's just a few notes there on characteristic functions. And one thing that you must also be ready for, looking for this, something you must be ready for in a case where remember, like I said, you must just know if you want the characteristic function of x, right? Suppose we're told that the PMF of x was simply just equal to 1 over 3, 1 over 3, 1 over 3, and 0. This is when x is 0, x is 1, x is 2, and otherwise it's just equal to 0, right? Suppose that was the case that we were given there. And now what we want is the characteristic function of x. By definition, we know this is equal to e to the power itx, right? But remember, like I was saying, it's not always the case that you'll be able to find these functions using these definitions here. But sometimes you have to do it manually. Fortunately, we're given the PMF in this case, and we can use the law of the uncontested decision. This is just something that I want you to watch out for, because unlike the PGF, where we are given something as expectation of s to the x, and then there's actually a manual definition that we're given, like this here. There isn't really something like that for the characteristic function, or something that I at least have. So the best way then for you to answer that kind of a question is using the law of the uncontested decision. And the way you do it is by simply saying this is equal to, because now our x is discrete, we are going to be summing, right, x starting from 0, right? I will say to 2, because that's what we're given there. And this is multiplied by e to the power itx multiplied by the px of x, like this. Which means what I would have is e to the it, my first x is 0, multiplied by 1 over 3, plus eit multiplied by 1, and my probability is 1 over 3, plus EIT times 2. My probability is also 1 over 3 in that case there. And then from there, you can simplify this here to find your answer. And your answer will be something in the form of, again, the final answer in this case it does not really matter. What I just wanted you to say is that's how you would approach a question where you will need to find the characteristic function and you're given in PMF in the range of x. But your answer would be something in the form of 1 over 3, 1 plus EIT plus E2IT. This is after getting the answer and then factorizing the common factor, which is 1 over 3. So if maybe you wanted to go further and find your expectation and your mean and stuff, I'll just give again for the expectation. We know that this will be equal to 1 over I, characteristic function, take the first derivative, let your t equal to 0, like that. And remember again, where your I is simply just equal to the square root of -1. Okay, cool. Yeah, that's it. That's just an example I wanted to outline there. And this one as well, not a full example, but just a few important properties of it that are there that I want to mention is that if you wanted to find, suppose, because you see the difference between what I'm going to do now and the one we did now is just that in the one we just did now, we're given a PMF, right? Which means this comes with probabilities. This comes with probabilities and also the range of your x. That's what we're given. But there could be a case where maybe you're just given the values of x to say that your x is equal to -1 and your x is equal to 1. If you look at this, if you look properly, if you look around your OTs, you'll find that maybe there's a group that got an OT which is like this here, where x is -1 and x is equal to 1, but it's not accompanied with the probabilities, so we were not able to use the formula, but to the approach that we just used now. And the best way you'll be able to do this here is to say this is by definition the characteristic function of our x here is the expectation of EITX, right? Then now you would have to use a property that you would have learned in MEM 1000, which tells us that e to the power IT is equal to cos t plus I and sine t, like that. Except that now what we have here is an expectation of ITX, which means that this here is actually just the expectation of cos, but instead of having just a t, it's cos tx plus I sine tx, like that. That's what you would end up having, something like this. And obviously, you can break this down to just the expectation of cos tx plus I, the expectation of sine tx. Okay, and then now you finding the answer to this here would just be a matter of getting averages, right? Because if you want the expectation of cos tx, and you know that it runs between -1 and 2 and 1, it's just 1. When x is 1 and x is also -1, it means for you to find the expectation, right, of cos tx, this is just a matter of you getting having cos t times 1 plus cos t and multiplied by -1 divided by 2, since there are 2 values that you're dealing with. So if there were 3 values, you would substitute them all as x and you divide by 3, like finding an expectation. Remember, that's like finding an average. And as I leave this section, I just want to also mention that to remind you that the cos of x, right, is an even function. It's an even function, something that might come up once in a while and be helpful. It's an even function, which means cos of -x is the same as your cos of x. This would become helpful here, where it's called cos minus t, which means this is also just equal to cos t. So all you have here is cos t plus cos t over 2, which is actually just equal to cos t. And your sine function is an odd function, which means this means that sine of -x is actually just equal to minus sine x, like that. So those are just a couple of things that are quite important under that section there. Cool, I think that's fine. Are you guys okay with that characteristic function? Does anyone have a question before I continue? Can I just get a reaction if you guys are cool and then I can continue? Okay. Cool. Awesome. Okay, let me continue now. The next part is just convergence. I'm gonna try because I can see we're already running out of time, but I also feel like that's quite an important section for us to look at. And convergence, we're just basically under this section, what we're dealing with is you have a sequence. It's mainly about sequences, right? You've got some sequence xn where your n is starting maybe from 1 or maybe even 2, but it's going all upwards to infinity or something like that. And now we're looking at the concept of this xn sequence converging to some number or constant xn. We're trying to see what that means, right? And we say that xn converges to x if the distance between this xn, the sequence, right, and the number we're saying it converges to. We say xn converges to x if the distance between them approaches 0 as n goes to infinity. So we have this sequence and we've got this number that we're assuming we are saying it converges to. And the definition of convergence now is saying that xn will converge to x if the distance between your sequence and this number you're saying it converges to becomes smaller as you increase your n. So that's basically the definition of sequence of conversion. You do this more when you do RA next semester, real analysis. And then yeah, what's important is that now when you're dealing with random variables as we are now, so that it becomes a problem that now this distance between x and your y, right? The distance between your x and y, which is dxy, like this, dxy, right? Because remember, we're saying xn converging to x. Now this is x converging to another random variable y, this which is equal to the distance between x and y. This is also a random variable when we're dealing with random variables. Because if this is a random variable and the random variable, the distance between them is also a random variable. Okay, that is just a statement that at the beginning of a note to try and relate this and that and just specify that, okay, but now this distance between the two is also a random variable. What's important actually now is just that there are 3 modes of convergence, right? So as we've defined what convergence is, and now we are saying there are 3 modes of convergence, right? 3 ways in which you can converge. The first one being almost surely, okay? And then this one here, almost surely, this is the strongest form of convergence. This is the strongest form of convergence. The one that follows there is in probability. You have convergence in probability. Then the other one is in distribution. And the reason I wrote that the one almost surely is the strongest is because I do want to then write another flow diagram there to show what I want to show now is that the strength will decrease as you go down, right? Which means that almost surely is stronger than probability, and in probability is stronger than in distribution. So if you've proven that something is converging almost surely, you can then assume that therefore it's converging in probability and in distribution. If you prove this one here, then this one is true. But if you've proven this one, it just means that this is true, and there's got nothing to do with whatever else that will be up on top. Cool. Then now there are ways to prove, to show if it's true or not. And because of time, I don't want to waste your time with the last 10 minutes that we have here. You definitely can find this in your notes, right? To say that, for example, what I mean is, so that you know what I'm not giving you now, is that, like, for example, to show almost surely, right? Show almost surely that the probability, this is just, you have to show that the probability of the limit as n goes to infinity of xn is equal to x is just equal to 1, right? So hence almost surely. So there are 3 things that are there in your notes to show when it's almost surely and to show when it's in probability and in distribution. Okay, and the one I want to quickly just refer to is the one for in distribution. That in distribution, when you say xn converges to x in distribution, right? This means that you need to show that the limit as n goes to infinity of the CDF of xn, right, is actually just equal to the CDF of x. So if you want to show that the sequence here, what you have, right, converges to X in distribution, all you have to do is to show that the CDF of your sequence will approach the CDF of X as n goes to infinity. But in most cases, this is very difficult for you to be trying to find the CDF of a sequence, right? Because yeah, it just becomes messy. It goes back to you to like that whole transformation section back in the chapters before. That's why instead of using this here, we hardly use this one. This would be a lot of work, and instead we substitute this here with Levis continuity theorem, right? Levis continuity theorem, and this theorem says that if x and n, this goes both ways. Xn converges to X in distribution. Then, like I said, this goes both ways if the limit as n goes to infinity of the characteristic function of xn t is the same as the characteristic function of x, like that. So if you've got some x, if you have some x, xn, right, and you are able to find the characteristic function of that xn, take the limit as n goes to infinity, and then from that you can conclude if the characteristic function is the same as that of x, you can conclude that xn converges to x in convergence. What I mean by that is that consider an example where we have some sequence bn, right? Bn for n equal to 0, 1, 2, going onwards like that, right? That's our sequence. And we are told that Bn has a binomial, is binomially distributed, and our P here is equal to lambda over n. Then you have that you've got another random variable B, which has got a Poisson distribution, and this is equal to, the rate is equal to lambda. And the question is saying that show that Bn converges to B in distribution, like this. That's what the question is asking you to do. Remember, the first definition, that the first condition, the first way that we are told to show this is to show that if you find the CDF of Bn, right? If you find the CDF of Bn, and then you take the limit as n goes to infinity, and also find the CDF of your B, they should be the same as n goes to infinity. If when you take this one going to infinity, then if you can show that, then you can conclude that this is true. But as you can imagine already, finding the CDF of a binomial distribution, okay, I guess maybe in this case it could be much easier because this is a commonly known PDF, but still, in most cases, it will be a lot of work. So instead, we can apply Levis continuity theorem, right? Which will tell us that if we should find the characteristic function of xn, right? And then when we find it, we'll take the limit as n goes to infinity. By definition, this is equal to the expectation of E ITX, like this, right? This is what we have by definition, part of xn. But what we know is that this is equal to actually the MGF of xn evaluated at what? IT. But remember that xn, I'm using xn, I'm so sorry, it's tendencies. We're looking for Bn, This is the sequence we're dealing with, Bn. And now what we have is that this is the MGF of our Bn evaluated at IT, but we know that Bn, right, has got a binomial distribution with n, and our P here is equal to lambda over n, like that, right? And then the next thing that we have to do is that we know the MGF of a binomial distribution, right? And MGF of a binomial distribution is Q plus P E to the Tn, like that. So what this is just telling us that the characteristic function of Bn is simply just the MGF of Bn, but evaluated at IT, which means all we have to now do is to say this is equal to Q, right, plus P, E, where there is T, we'll be substituting IT, and this all to the power n, like that, right? And then to continue from there, what this means is that, remember our P was equal to lambda over n, which means Q is equal to 1 minus lambda over n. So this is equal to 1 minus lambda over n plus lambda over n e to the it or to the power n. You can group this up together. Again, this might be something that you may not be able to think of like in a test on the spot, but since we've seen it now, it's something that when you get to something similar like this in a test maybe on Tuesday, you can it's an option you can consider that you're going to combine this all together so that you have one thing, one term that is 1 plus you have your n, and you're going to have a lambda out here e to the power it minus 1 all to the power n. And the reason why there's a plus here, I simply just started with this term and then I took the minus 1 that side, hence the minus 1 and the lambda that are here. Otherwise, I have not done anything fancy there. I just swapped them and I combined these two here, which has got a denominator of n. Okay, I hope that's cool. Then the next thing from there is the use of one of the properties that I stated, although that were in workshop 1, but I'll say it, I'll write down again, which tells us that the limit as n goes to infinity of 1 plus x over m to the power n is equal to e to the power x. There's a property which tells us this, right? And now this answer that we have there is actually our characteristic function of the sequence bn as we have there. And remember, for us to show that xn converges to x in distribution, we want to show that the characteristic function of bn as n goes to infinity will actually just be b there, and that means I have to take the limit as n goes to infinity of the characteristic function of this, right? Which we got as being 1 plus lambda e to the power it minus 1 over n, like that, or to the power n. Using this property, my answer will then just be equal to e lambda eit minus 1, like that, or to the power n. Using that property, then I'll get that answer, right? So now I have my characteristic function as n goes to infinity. And for me to conclude my answer that the two converge in distribution, it means that I just need to show that the characteristic function of b is actually just the same as that. And by definition, this is equal to the expectation of EIT B. Again, this is equal to the MGF of B now evaluated at IT. And remember, B here in the information there was that it has got a Poisson distribution with my lambda, which means this MGF, which we know is equal to e to the power lambda and e to the power t minus 1 to the power n, right? I'm not sure, you can just confirm that. I'm not sure if there's this n here. Oh, no, there isn't this n. There isn't this n. Actually, there isn't this n, because remember, even here, I just took this to just being e to the power x, but not the n. So here, what I just have is that, and even for my MGF of a Poisson is given like this with the formula sheet, then I have this answer. And then now you can tell that these here are the same. Except that obviously there's an IT there, but you can see that it's the same structure of the what you call this thing that we're using now, the characteristic function. Therefore, you can conclude that the sequence Bn actually converges to B in distribution. Now, the same thing, because in most cases, the one that you'll be asked to prove is the one in distribution and in probability. That's the one that I'm mainly asked. The same way that we were using the characteristic function, there's also one theorem, doesn't really have a name though, but it says that if xn converges to x in distribution, right? This goes both ways, that you can show that the limit as n goes to infinity of your MGF of xn is the same as the MGF of your x, like that. So the same way we're finding the limit as n goes to infinity of the characteristic function, you can actually just do the same for the limit as n goes to infinity of your MGF. The only thing is that when it comes to the MGF, there are a few tricks that you have to do, right? Unlike the characteristic function, I personally feel like the characteristic function one is usually, I feel like it's the neatest way, but again, you could get a question which will force you to use the moment narrating function approach. And the only tricks is that you get to a point where you always need to take the ln, okay, I remember the log of the function, right? So because of time, guys, can you please just find some questions, right, on this year? Definitely 2019 charts. You should find a couple of questions this year, and even the chart questions. I think it's chart 5 or something like that. You'd find questions where we prove this using that. And the tricks are, like I was saying, the first part, you would have to take a log, right? You set the normal way, your MGF of xn. By definition, you use a definition. Then when you get to a point where you take the log of whatever you have, so that especially when you have e to the power something, you take your logs to bring stuff down. And then the reason we take the logs is because under this approach, we would want to use Taylor approximation, right? Taylor approximation, right? If I'm saying correctly. And this year, what should come to mind is that e to the power x is simply just equal to 1 plus x squared over 2 factorial plus just going onwards like that, right? So this is something that you should just check out. This will always come true. And another one is in convergence and probability. And the property that we will use here to prove that is the Chebyshev's inequality. If you remember, I always start, whenever we get to this part in chapter 2, I always mention on how we would use this in under convergence, which tells us that the probability that xn, this big random variable xn minus its mean are greater than some k, which is a positive, is less or equal than the variance of your x over this here k squared. Okay, and I understand that we've reached 6 o'clock now, but can you please look at this example here? It explains it properly. There's this example which you find in your 2018 OTs where there is some process SR like this. I just want to refer you guys to that because it's very helpful to understand this. There is you've got some process NS like this, but now you have to show that this process divided by that will approach to lambda in probability, right? And for you to show this, as you would say under the conditions on how to prove convergence and probability, you would have to show proving convergence and probability on its own. Before I go any far, we have to show that the limit as n goes to infinity of the probability of xn, right? This xn, this sequence minus x, right, is greater than some epsilon is equal to 0. This is what you have to show, right? And in order for us to show this, in our case now with this process, what we just have to show is that the limit as n goes to infinity of the probability, instead of saying xn now, is this process that we want. That is n SR, right, divided by absolute value of SR like this. So what the distance between that and this lambda that we were dealing with here being greater than some epsilon, and this should just be equal to 0. Okay, and you would need to use Chebyshev's inequality in this case, and the manner in which you would do it is that you would want to translate it into a problem where you are looking for a probability where you are saying the x minus its mean, right? And there was more information about this here is that this was a Poisson distribution, and its mean was equal to lambda times SR, like that. So the only way that you can now get the mean, you can translate this into a Chebyshev's inequality problem, is for you to say the process minus its mean. And the way you can actually get the mean of this process here is by multiplying the bottom here, so that you would this term inside will just become n SR, right, minus lambda SR being greater than SR epsilon, like that as well. I know this is a little bit messy, but again, like I was saying, this you would find it in a 2019 OT. I'm not sure what number of the OT is exactly, but the most important thing is how with convergence and distribution, was the main ones that you would find to prove is the convergence and distribution and convergence and probability. And the important thing about the one in distribution is that instead of saying taking the limit as your CDF goes to infinity to show that it's the same as the CDF of what you're saying it converges to, rather use Leibniz continuity theorem, where you're going to use your characteristic function Or if you are more comfortable with your MGF, rather use the MGF, so you're going to take the limit as n goes to infinity of your MGF, and it should be the same as the MGF of what you are saying it's converging to. And when it comes to the one in probability, that is convergence in probability, most of the cases you actually then have to use Chebyshev's inequality, which is that. So my best advice is now just try and look around for more questions under this topic. Unfortunately, in my year, this section was not examinable because it's more maths stuff, which is in RA. So this is just best as I could find just to talk a little bit about it. You probably have more information than I do, but I just hope the little I gave you for this will be helpful. And yeah, I think that's it. Wish you guys the best for your tests and exams. Hope to see you soon. Cheers, guys. Cool.